Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. In the beginning, there is nothing. No space, no time, no light. Only a void without form, a stillness beyond imagining. Yet in this emptiness, a potential stirs. Then, a spark. A single searing point of infinite density and heat, igniting existence. In an instant beyond time, I am born. At that instant of birth, all that would become space and time was compacted into an unimaginably small point. It wasn't a speck expanding into space. It was space itself expanding. There was no outside into which to explode, no before in which to have existed. The laws of physics as we know them were straining under the extreme conditions, temperatures and densities so high that our current understanding breaks down. In that first infinitesimal tick of time, the Planck epoch, a mere 10 to 43 seconds, gravity, electromagnetism, and nuclear forces may have been unified into one. Cause and effect, space and time, all were scrambled in a quantum haze. But as soon as I emerged, I began to evolve, to cool and differentiate. As things cooled, forces likely separated. Gravity had already broken away from the others during the Planck epoch, and now the strong nuclear force split off from the electroweak force. Eventually, the electroweak force itself divided into the electromagnetic and weak forces by the end of the first fractions of a second. These transitions set the stage for the physics we know today, with four distinct fundamental interactions. Cosmic inflation. In my first infinitesimal moment, an era unfolds that defies imagination. I undergo a sudden flash of expansion, a brief, furious growth called inflation. In far less than a heartbeat, I swell from smaller than a grain of dust to cosmic proportions. Space stretches faster than light can chase it, for even light is newborn and finding its way. Distances that were subatomic become light years vast in the merest whisper of time. It is a silent cataclysm, an exponential surge smoothing out any wrinkles of existence. To put it in perspective, in far less than a trillionth of a second, the universe may have doubled in size over and over, perhaps 100 times or more. Something the size of a quantum particle ballooned to the size of a grapefruit and kept going. This tremendous stretching explains mysteries that would puzzle future cosmologists. How the universe became so smooth and uniform on large scales, and why space is so nearly flat, not curving in on itself like a sphere, nor curving outward like a saddle. Inflation ironed out any curvature and mixed far-flung regions so that they all shared the same conditions before being hurled apart. Thus, when our telescopes look at opposite sides of the sky and see nearly the same temperature after billions of years, it is because those regions were once intimately close, just before inflation tore them apart faster than any signal could catch up. The imprint of this era can be seen in the cosmos even today. The tiny ripples in density that inflation amplified are visible as faint irregularities in the microwave background, like a baby picture of the universe revealing the seeds from which galaxies would grow. Yet even in this nearly uniform burst, perfection is not absolute. Tiny quantum fluctuations, minuscule tremors in the fabric of what is, ride along the expansion. These are random microscopic whispers of density, here a touch more, there a touch less. Inflation grabs these specks of imbalance and stretches them enormously. What were once quantum wrinkles are now cosmic seeds, faint imprints laid into the newborn universe. Though I am almost featureless in this early rush, those seeds will one day grow into galaxies and clusters, the grand scaffolding of structure. The blueprint of the night sky is drawn in these first trembling instants, an unseen pattern that gravity will soon trace out. Birth of particles. As the violent inflationary surge settles, Its immense energy transforms into matter and light. I am now an ocean of particles, a roiling plasma hotter than a billion suns. Quarks, the tiniest sparks of matter, dance chaotically with antiquarks in the intense heat. For every particle, an antiparticle twirls in mirror step. When these twins meet, they vanish in a flash of pure energy. Matter and antimatter annihilate in a furious balance, flooding me with radiation. Yet, by the subtlest of odds, this dance is not perfectly symmetrical. For every billion pairs that destroy each other, a single particle survives without a partner. That tiny excess, one fleck in a billion, tips the scales in favor of matter. It is that scant residue that will become everything of substance. Every star, every planet, every living being, built from those surviving pieces of me. Milliseconds and seconds tick by as I expand and cool just enough for quarks to find companionship. They bind together in trios, forging the first protons and neutrons. A seething nucleus forms here and there as these nucleons cluster. By the time I am mere minutes old, an epoch of creation unfolds, nuclear fusion in my primordial fire. Protons smash together with neutrons, assembling the lightest of elements. Hydrogen is born, just a single proton at its core, and helium, with 2 protons and 2 neutrons, joins it. Trace amounts of lithium sprinkle in as well. In those first 5 minutes, I fabricate the basic ingredients of chemistry, a cosmos now composed of about 3/4 hydrogen and 1/4 helium, with only traces of anything else. It is still far too hot for complete atoms to form. Electrons remain free, careening through the plasma, and the cosmos remains an opaque, glowing fog. But the recipe for future stars and galaxies is set. I am a glowing, opaque sphere of blinding plasma, filled with light and newborn matter, expanding rapidly outward. During these first moments, not only quarks, but other exotic particles flooded the scene. Leptons like electrons and their antiparticles, positrons, formed a hot sea, and ghostly neutrinos streamed through the density almost unhindered. The universe was a roiling cauldron of particles constantly transforming, matter to energy and back again, as temperatures were trillions of degrees. Quarks, which had never known confinement before, suddenly felt the tug of the strong force as the expansion cooled the fireball just enough. They clumped into protons and neutrons, each made of 3 quarks locked together. Around 1 second after the Big Bang, it became cool enough that neutrinos, extremely light particles, decoupled and began traveling freely through space, carrying with them a fossil record of that early moment, a cosmic neutrino background that still permeates space, albeit nearly undetectably. By about 10 seconds in, the temperature dropped to the point that electrons and positrons annihilated almost entirely, leaving a slight excess of electrons that would later form atoms. From that point on, photons, particles of light, were the dominant form of energy in the cosmos, bathing everything in a brilliant glow. In the following minutes, an era of primordial nucleosynthesis unfolded. The protons, hydrogen nuclei, and neutrons collided and stuck together in nuclear reactions. A proton and neutron fused to make deuterium, heavy hydrogen. Deuterium fused into helium. For a brief time, conditions were just right for forging nuclei. About 1/4 of the mass of the universe turned into helium-4, 2 protons and 2 neutrons per nucleus, because nearly every neutron found itself bound into a helium nucleus. Any lone neutrons decayed into protons. A trace of deuterium, helium-3, and a smattering of lithium and beryllium were also created. But within about 5 minutes, the expansion cooled the plasma so much that these nuclear reactions faltered. The furnace of element formation shut off, having left a newborn universe chemically simple, roughly 75% hydrogen and 25% helium by mass, with only the tiniest sprinkling of other light elements. This primordial recipe has been confirmed by observations eons later. When astronomers measure the composition of the oldest stars and distant gas clouds, they see precisely this ratio, a fingerprint of the Big Bang's opening act. By 1/2 hour old, the universe is a hot, bright fog of subatomic particles and radiant energy. The drive of expansion continues to cool this fireball. Photons still scatter off electrons constantly, so the universe is opaque like the inside of a star. But as millions of years pass, the relentless expansion causes the sea of radiation to lose energy and the plasma to thin and cool further. The blaze dims. First light. The cosmic microwave background. For a long while after those first furious minutes, I remain a brilliant, hot fog. Intense light, photons, ricochets through a dense thicket of charged particles trapped in an endless pinball game. Any ray of light travels only a hair's breadth before colliding with an electron or nucleus, scattering in a new direction. I am bright but opaque, a shining cosmos that no outside observer, if one existed, could see into or through. A bright orange-white glow permeates everything, but it is imprisoned by the particles that fill me. Time flows on. Expansion and cooling continue their inexorable course. Hundreds of thousands of years pass. From the perspective of my now vast self, this is an eternity, though I am still an infant by cosmic standards. At roughly 380,000 years old, a pivotal change occurs. The sea of particles has cooled enough for electrons to slow and be captured. Those free electrons, once the jailers of light, combine with protons and helium nuclei to form neutral atoms. Hydrogen and helium finally hold their electrons in orbit, and with that, the blinding fog thins and vanishes. Space goes from opaque to transparent. In an instant, my entire being is filled with a gentle glow that is free at last to stream unimpeded. This is my first light, the earliest light that will ever shine through me. A warm afterglow of creation. It floods outward in all directions, carrying with it a perfect snapshot of my infant state. No longer trapped, the light races through expanding space, a cosmic broadcast heralding the next chapter of my story. That primal glow, born in this moment of liberation, will faintly persist for billions of years. Even in the far future, its memory will remain as a cool whisper, only 2.7 degrees above absolute zero in the microwave spectrum. This cosmic microwave background is the oldest light in the universe. Today, it is a cold 2.725 degrees above absolute zero glow, detected by sensitive radio receivers as a nearly uniform microwave hiss across the sky. But at the moment of its release, it is a diffuse, soft firelight, illuminating a universe grown vast and calm enough for light to at last roam free. After this epoch of first light, the universe again is dark to human eyes. The brilliant glow of the infant cosmos is quickly stretched by expansion into invisibly long wavelengths. No new stars yet exist to shine. The universe enters a deep cosmic night, known as the Dark Ages. Yet within that darkness, something vital is happening quietly. Gravity is beginning to sculpt the structure that was imprinted in those earliest moments. Gravity takes over stars and galaxies. Ignite. My matter is ever so slightly uneven. Here, a denser patch. There, a more rarefied one. Though the differences were once infinitesimal, gravity is patient. Over tens of millions of years, the denser regions draw in more and more gas from their surroundings. Filaments of matter begin to form, bridging between clumps and threading across vast distances. An immense cosmic web takes shape, invisible threads of material weaving a scaffold throughout space. At the nodes of these filaments, matter pools like dew collecting at the intersections of a spider's web. Those knots grow denser and hotter as gravity squeezes them tighter. For the next 100 to 200 million years, the universe remains devoid of new light. It is a cold, transparent expanse filled with dim clouds of hydrogen and helium, gradually coalescing into filaments and clumps. Then, at last, the silence is broken. Deep within one of the densest clouds of gas, gravity ignites the first star. A pocket of hydrogen, after collapsing under its own weight, reaches temperatures of millions of degrees in its core, and nuclear fusion begins. A brilliant newborn star flickers to life, pouring light and heat into the surrounding gloom. One by one, more stars follow, an entire generation of giants blazing hot and blue. They gather in clusters, illuminating pockets of the darkness. Their radiant energy begins to clear away the remaining wisps of hydrogen fog around them, carving out bubbles of transparency in the dark cosmic sea. The epoch of reionization has begun. Starlight is reawakening the transparency of space at shorter wavelengths. Those pioneering stars, astronomers call them Population 3, have no heavier elements to aid in cooling their gas, so they grow truly massive, 30, 100, perhaps even 300 times the mass of our Sun. They burn their fuel quickly and furiously, millions of times brighter than the Sun, but in only a few million years, many, the very massive ones, will exhaust their core fuel. In a few million years, many will explode as supernovae, seeding the surrounding space with heavier elements forged in their hearts. These first stars are beacons marking the end of the cosmic dark ages. They are massive and short-lived, and when they die, they do so spectacularly. Some as supernovae, perhaps some collapsing directly into black holes. Over several 100 million years, the first stars collected into the first proto-galaxies, small fledgling versions of the galaxies we know. Gravity continues its work, drawing these stellar clusters together into nascent galaxies. Small proto-galaxies merge into larger ones, their combined light forming the first glimmers of the grand galaxies that will populate my expanse. As these early galaxies assemble, ultraviolet light from the first stars and emerging quasars, bright black holes, breaks down the remaining neutral hydrogen in space. Gradually, the ultraviolet glow of youthful galaxies ionizes the gas in the universe's vast reaches. Over several 100 million years, starlight travels farther and farther, punching through the once pervasive hydrogen fog. By the time the universe is about 1 billion years old, this process of reionization is essentially complete. Stars and galaxies have transformed the early cosmos, making it transparent to even high-energy light. The cosmic dark ages have given way fully to a new dawn of cosmic illumination. The universe is now recognizable in form. Dark matter scaffolds, glowing galaxies, and expanding space, much as we observe it today, just younger and smaller. Gravity has woven a feathery web, and along its threads, the first galaxies shine. Those initial massive stars that lived fast and died young left a lasting legacy. They created, in their brief lives, the first heavy elements like carbon, oxygen, and iron. When they perished, they scattered these elements into the surrounding gas. That enriched gas, in turn, began to collapse into new generations of stars. Some of the earliest stars also likely collapsed into black holes when they died, seeding the centers of growing proto-galaxies with dark hearts. These black holes, formed so early, might have become the seeds for the supermassive black holes we find in galaxy centers today, providing gravitational anchors for building galaxies. Thus, the early universe's simplicity is giving rise to complexity. The first stars and galaxies are transforming the smooth primordial gas into a cosmos laced with structure and light. The long night ends in countless points of starlight. The cosmic web is alive with the flow of gas into galaxies, stars bursting into existence, and the stirrings of planets around those stars. Vastness, the scale of the cosmos. Now the canvas of creation is rich with structure. Galaxies blaze like islands of light in a vast sea of darkness. I hold perhaps hundreds of billions of galaxies in the patch of me visible to you, and there may be more beyond. Each galaxy is a glittering city of stars, majestic spirals with graceful curving arms, or giant ellipticals with swarms of suns in random orbits, or irregular firecracker galaxies clumping in odd shapes. A typical galaxy might carry hundreds of billions of stars in its whirl, each star a sun with its own potential retinue of planets. These galactic isles are separated by tremendous gulfs of nearly empty space. To journey from one galaxy to another, even at the speed of light, would take millions of years, crossing the silent darkness between. Galaxies do not stand alone. They gather in families, groups of a few or clusters of hundreds to thousands, bound together by gravity. Within these clusters, galaxies dance around a common center, tugging at each other in slow gravitational ballets. Sometimes they draw too close and merge, two galactic cities becoming one, their stars passing like intermingling swarms of fireflies. Beyond the clusters, on still larger scales, galaxies are arranged along the filaments of the cosmic web. Superclusters of galaxies link in chains and sheets, spanning hundreds of millions of light years. In some regions, colossal walls of galaxies stretch out, structures so vast it takes light 1 billion years to traverse them. Between these luminous filaments lie voids, enormous expanses where almost nothing exists, darkness spanning tens of millions of light years, with only the occasional stray galaxy or atom in the emptiness. It's almost beyond imagination. The observable universe contains more than 100 billion galaxies, perhaps as many as 2 trillion, and each galaxy can have hundreds of billions of stars. The number of stars in the observable universe is on the order of 10 to the 22, roughly 10 billion trillion. That's a quantity comparable to the number of grains of sand on all the beaches of Earth. If each star were a single grain of sand, the stars of the observable universe could build entire worlds of sandcastles. Yet we have catalogued only a tiny fraction of these stars. The rest gleam as distant points of light, reminders of how much remains beyond our reach. To appreciate the vast distances, the nearest star beyond our Sun is about 4 light years away, which in human terms is nearly 40 trillion kilometers. Our fastest spacecraft would take tens of thousands of years to reach it. And that is just next door, cosmically speaking. The Milky Way galaxy alone is 100,000 light years across. Even a beam of light, the fastest thing in existence, takes 100 millennia to travel from one end of our galaxy to the other. The Milky Way contains perhaps 300 billion stars. It is one of over 50 galaxies in its small neighborhood called the Local Group, which spans about 5 million light years. The Local Group, including our Milky Way and the Andromeda Galaxy, is itself on the outskirts of the Virgo cluster of galaxies, tens of millions of light years across. The Virgo cluster, in turn, is part of the Laniakea supercluster, an even larger grouping spreading over 500 million light years. And even that is just one filament in the cosmic web. Above scales of a few billion light years, the universe starts to look the same everywhere, homogeneous and isotropic, an expanse of countless galaxies amid yawning voids. Between the galaxies, the voids are impressively empty. A typical intergalactic void might be 100 million light years across, with almost no galaxies inside. The density of matter in such a void could be as low as a few atoms per cubic meter, so vacant that a physical vacuum chamber on Earth would be denser. These immense vacuums and luminous filaments together create a frothy structure when viewed on the grandest scale. If we could zoom out far enough, the cosmic web would appear like lace or foam, filaments and walls of galaxies outlining enormous bubble-like voids where hardly any matter resides. Each bright knot in that web is an entire galaxy or cluster of galaxies. while the purple or dark gaps in between are the scarcely populated voids. Zooming out to behold all of this at once, the large-scale structure of the cosmos emerges as a sort of cosmic tapestry, a pattern nearly 14 billion years in the making, a cosmic web immense yet delicate. From the tiny quantum ripples in my infancy has grown this immense network of clusters and voids. The scale of it defies comprehension. Stars, planets, and life are nestled in galaxies, which are themselves mere motes in this grand design. And yet, for all its immensity, this structure is still young, still evolving. The cosmic web sways and stretches as I continue to expand. It is a living map of gravity's handiwork, a portrait of vastness that invites both awe and humility. The dark universe. Hidden mass and energy. Yet, all the brilliance of stars and galaxies, all the glowing gas and dust that can be seen, is only a tiny portion of my story. Much of me is shrouded in darkness, not just the darkness of empty space, but the darkness of unseen substance and unknown energy. I am, in fact, built and governed largely by things that human eyes and instruments cannot directly detect. This is the dark universe, and it makes up the lion's share of my being. First, there is dark matter. It is a mysterious, invisible form of mass, utterly transparent and elusive. Dark matter does not shine or absorb light. It neither glows like stars, nor blocks starlight like dust. Yet it is there, revealed by its gravitational pull. From the rotation of galaxies to the motions of clusters, dark matter's gravity holds them together. Without it, galaxies would fly apart. Their stars move so fast that visible matter alone could not tether them. This unseen mass forms the backbone of the cosmic web. Long ago, its gravity gathered the primordial gas, helping seed the first stars and galaxies. Even now, halos of dark matter envelop galaxies like cocoons, and great clumps of it anchor clusters of galaxies, bending the path of light that passes nearby. By the best measurements, dark matter outweighs normal matter by about 5 to 1. For every pound of atoms, there are roughly 5 pounds of dark matter lurking unseen. All the luminous stars, planets, and nebulae are mere frosting on a cake of dark matter. What is this dark matter made of? I, the universe, keep that secret close. It might be some exotic particle that seldom interacts, or something stranger still. It remains one of the great mysteries of my nature, an enigma slowly yielding clues but not yet fully uncovered. Over the decades, numerous experiments have been devised to detect dark matter particles directly. Physicists have set up large detectors in deep underground laboratories to shield from cosmic rays, hoping to see a rare interaction between dark matter and regular matter. They have yet to find a definitive signal. Dark matter remains elusive, so far observed only through the pull it exerts on the visible world. One dramatic piece of evidence for dark matter came from observing galaxy cluster collisions. In one famous case, 2 clusters of galaxies passed through each other. The hot gas in them, normal matter, interacted and slowed down, but the bulk of the mass did not. By mapping the gravitational field of this collision, using gravitational lensing of background galaxies as a probe, astronomers found that the mass had separated from the gas. The invisible dark matter slid through the collision unaffected, while the normal matter, the gas clouds, lingered behind, dragged by friction. The result was a spatial separation between where most of the visible mass was and where the gravitational mass was, clear proof that an unseen substance dominated the mass of those clusters. The nature of dark matter is a great enigma. It could be a new type of particle, perhaps similar to neutrinos, but far heavier and slower, a so-called WIMP, weakly interacting massive particle. Or maybe an ultralight particle field pervading space, sometimes called axions. Some even speculate it could include primordial black holes formed in the Big Bang's chaos. Each hypothesis is being tested, but none has been confirmed. As our detectors become more sensitive and our telescopes map dark matter's influence in finer detail, we inch closer to an answer. Until then, dark matter is a reminder that most of the universe's content is literally invisible to us, except for its subtle gravitational whisper. And then there is an even more baffling darkness: dark energy. If dark matter is an invisible scaffold holding me together, dark energy is an invisible hand pushing me apart. For many years, scientists thought my expansion was slowing under gravity's pull, but in 1998, astronomers found that certain distant supernovae were fainter and hence farther away than expected. They concluded this could only happen if those supernovae and their galaxies had accelerated away faster as time went on. The discovery of this accelerating expansion was revolutionary. They suspect a mysterious something fills space, acting as a repulsive gravity. Dark energy wasn't discovered until the late 1990s, but its influence began billions of years earlier. Roughly 5 billion years ago, about when our sun formed, dark energy's effect overtook gravity on cosmic scales and expansion started speeding up. Today, dark energy is the dominant component of the entire universe. By current reckoning, about 68% of the universe is dark energy, 27% is dark matter, and only 5% is normal matter. In other words, everything we detect directly, galaxies, gas, dust, us, amounts to a mere 1/20th of the cosmic pie. The rest is hidden. What exactly is dark energy? The short answer is, we don't know. The leading idea is that it's a property of space itself, often represented by the cosmological constant. In Einstein's general relativity equations, a cosmological constant is a term that gives empty space an intrinsic energy. Einstein once introduced such a term to allow for a static universe solution, then called it his greatest blunder when expansion was discovered. But it appears something akin to Einstein's cosmological constant is real after all. If dark energy is this constant vacuum energy, then as the universe expands, new space brings more of this energy, causing expansion to fuel itself in a feedback loop. Alternatively, dark energy might be a dynamic field, sometimes dubbed quintessence, that changes slowly over time. If it were to strengthen in the future, it could tear the universe apart in a big rip. If it were to decay, it might eventually halt or reverse expansion. But so far, observations of distant supernovae, cosmic expansion history, and the cosmic microwave background suggest dark energy behaves very much like a constant energy of space. It's as if every cubic meter of vacuum holds a tiny amount of energy that, when multiplied by the vast volume of space, drives the acceleration. Dark energy is even harder to grasp than dark matter. At least dark matter clumps and pulls on things. Dark energy, by contrast, is a smooth, diffuse pressure that doesn't form structures or have local effects we can feel. Its presence is known only through the geometry of the cosmos. Their main similarity is that we don't yet know what either one really is. For now, they are names for phenomena we observe without fully understanding. We can only watch as dark energy relentlessly pushes and dark matter quietly tugs, shaping my fate. Thus, I am both light and dark. The cosmos you perceive, the stars and nebulae, are just the glittering foam on a deep, dark sea. Beneath and between that light lies the majority of my substance and the key to my destiny. The dark universe is my shadowy foundation and the silent driver of my expansion, reminding any who explore my depths that not all can be seen, and much remains to be discovered. A living cosmic web. Structure in motion. The cosmic web is not a still tapestry hung in space. It is alive with motion. Every galaxy within it is on the move. Stars orbit the centers of galaxies in stately rotations, and those galaxies, in turn, waltz within clusters. Clusters themselves drift subtly under the gravitational pull of larger-scale structures. It is a cosmic dance spanning billions of years per step. Galaxies stream along filaments of gravity, drawn toward the dense hubs where clusters form. Like leaves carried by slow currents, whole galaxies migrate along these invisible rivers of force, falling inexorably toward the nearest concentration of mass. In some regions, hundreds of galaxies swarm around a cluster's center, a great metropolis of galaxies, each swirling to the music of gravity's pull. Between clusters, filaments channel gas and galaxies inward, much as capillaries feed blood to organs. This vast web of matter behaves almost like a living organism. It has a skeleton, the dark matter filaments, and arteries, the flowing gas and infalling galaxies. Some have even noted an uncanny similarity between maps of the cosmic web and networks of neurons in a brain. Two vastly different scales yielding a comparable web-like architecture. It's as if the universe has a structural nervous system, galaxies as glowing neurons, and filaments as connecting strands. Galaxies interact like cells exchanging material. When they pass through clusters, hot gas can be stripped from them. When they collide, they swap or trigger new bursts of star formation. Outflows from supernova explosions and active black holes in galaxies spread chemical nutrients, heavy elements, into the surrounding medium, enriching the cosmic environment. There is a kind of metabolism at work. Matter cycles in and out of galaxies. Over billions of years, structures grow, merge, and transform. Small galaxies are consumed by larger ones, a process colorfully called galactic cannibalism. Clusters collide and coalesce into even larger clusters. The cosmic web itself slowly changes shape, its filaments becoming more pronounced in regions where gravity pulls strongly, while expanding space pries some structures apart in others. In this sense, the universe is not static, but a dynamic, evolving network. Even our own galactic neighborhood participates in this grand ballet. The Milky Way and Andromeda, our nearest large galaxy neighbor, are falling toward each other and will merge in a few billion years, following the choreography set by the gravitational lines of the web. Our local group of galaxies is being drawn toward the Virgo cluster, which in turn flows toward an even larger concentration of mass, sometimes called the Great Attractor. Everywhere we look, we find evidence of movement, streams of stars in our Milky Way halo, marking the remnants of devoured dwarf galaxies, galaxies with tidal tails, stretched ribbons of stars, testifying to past close encounters, clusters with gas shock fronts, soundless sonic booms from recent collisions. The cosmic web lives and breathes through these motions. Though the timescales are immense, change is constant. My large-scale structure today is different from what it was eons ago, and it will continue to evolve. The web of galaxies grows more complex in some places, emptier in others, an ever-shifting balance of creation and dissolution. It is a grand ecosystem on the scale of the universe, a living web that connects every galaxy to the fate of the whole. Interestingly, the universe was more actively forming stars a few billion years after the Big Bang than it is today. Galaxies had a cosmic springtime of star birth around 3 to 4 billion years into the universe's life, 10 billion years ago, when cold gas was abundant and collisions frequent. Since then, star formation has generally declined. The universe is in a quieter, middle-aged phase. Many massive galaxies have settled into a passive existence, shining with the diffuse red glow of old stars, while smaller galaxies continue to form stars, but at a slower rate. The bright blue cosmic noon has transitioned to a more golden afternoon. In the far future, star formation will slow to a trickle as gas grows scarce, and the universe will gradually dim, entering a long twilight. But in this current epoch, galaxies across the universe still display a glorious variety, from youthful spirals with luminous nurseries to massive ellipticals full of ancient stars. Time. The flow and nature of time. Time is the medium of my story. It was born with me in that first moment. Before the Big Bang, there was no before in any meaningful sense. I carry time within me just as I carry space, the two woven together into space-time. From the ticking of atomic clocks to the slow drift of galaxies, time is the ever-present river in which all events occur. It flows ever forward, carrying us from my past into my future. But time is not as rigid as everyday experience suggests. It can stretch and bend. When you move at speeds approaching the speed of light, or when you dwell in the intense gravitational embrace of a massive object like a neutron star or black hole, your experience of time slows relative to the rest of the universe. A fast-moving spaceship's clock might tick slower than those left behind. A second near a black hole's edge might correspond to hours or years far away. This is the strange flexibility of time described by relativity. Space and time adjust so that the cosmic speed limit, light speed, is never broken. To accomplish this, time itself can dilate, different for different observers, depending on their motion and gravity. Each observer feels time flow normally for themselves, yet their clocks can disagree when compared after a journey. It is as if time has personal rhythms, yet all are part of one grand cosmic symphony. We have measured these effects. Precise atomic clocks carried on aircraft or satellites tick at different rates compared to those on Earth, requiring GPS systems to account for the difference. Particles called muons, created in the upper atmosphere by cosmic rays, live much longer as they race toward Earth's surface at high speed than they would if at rest, because time, from our perspective, runs slower for them. Astronauts who spend months in orbit age ever so slightly less than those on the ground. The universe's code allows such deviations, and we have verified them, time and again. Nature herself has conducted the experiment to show Einstein's relativity in action. And yet, despite these malleable rhythms, time has one inexorable direction. Why does it always march forward, never backward? The arrow of time is tied to the growth of entropy, disorder. The universe started in a very ordered state and has been moving toward greater disorder ever since. In my youth, I was hot, dense, uniform, and low in entropy. As I expanded and evolved, entropy increased. Structures formed even as the overall mix became more even. Eggs break, but broken eggs do not spontaneously unbreak. Stars burn their fuel and increase entropy, but the ashes of their nuclear fires do not reassemble into fresh hydrogen. It is the one-way increase of entropy that gives time a direction, from past to future, from order to disorder. Memory works in one direction. We remember yesterday, but not tomorrow. In that asymmetry lies the reason we perceive time as flowing forward. But what is time, truly? Is it a fundamental ingredient of reality or a convenient illusion that emerges from change? Physicists ponder whether time could be emergent, a byproduct of something deeper, perhaps quantum entanglements or a timeless block geometry of space-time. Others envision time as a dimension much like space. They imagine that the past, present, and future all coexist in a block universe, where every moment is another coordinate in space-time. In that lofty view, time doesn't flow. Instead, we who dwell within experience it as flow because we move through this block, slice by slice. For me, as the cosmos, perhaps all eras of my existence, my fiery birth, the present moment, and even my far future are already woven into my fabric, each chapter indelibly part of the whole. Or perhaps time is genuinely unfolding, with the future undetermined until it becomes present. Philosophically, time is mystery and paradox. It is the source of change, the healer of wounds, the eroder of mountains. It ensures that not everything happens at once. Within me, time allowed complexity to rise from simplicity, turning a uniform fireball into a structured cosmos teeming with wonders. Without time's arrow, cause and effect would break down, and evolution, cosmic and biological, could not proceed. And what of the end of time? In the distant future, if all processes cease, If stars die out and particles decay, time would become nearly meaningless, for nothing would mark its passage. A second, or a trillion years, would be moot in a truly frozen cosmos. These musings have no definite answer yet. But for now, time is the ever-beating heart of the universe's narrative, the rhythm to which all cosmic events dance. Through time, I transform and unfold, moment by moment, eon by eon, an ongoing story linking what was to what is and what is yet to come. Stars and elements. Cosmic alchemy. Stars are the alchemists of the cosmos. They take the simplest element, hydrogen, forged in the Big Bang, and fuse it into heavier elements. Deep in the cores of stars, under crushing pressure and intense heat, hydrogen nuclei merge to form helium. This process, nuclear fusion, releases the light and warmth that make stars shine. For most stars, this is the central drama of their lives, turning hydrogen into helium over billions of years. If a star is massive enough, it pushes the alchemy further. After exhausting hydrogen, it begins to fuse helium into carbon and oxygen, elements essential for life as we know it. In larger stars, the burning continues in successive stages. Carbon fuses into neon and magnesium, neon into oxygen, oxygen into silicon, and silicon into iron. Layer by layer, like the rings of an onion, the star builds an internal structure of elements. Each fusion reaction releases energy until it reaches iron. Iron is a dead end for fusion. Fusing iron atoms consumes energy instead of releasing it. So when a star's core accumulates too much iron, it's a sign of imminent catastrophe. For the Titanic stars, those more than about 8 times the mass of the Sun, reaching an iron core triggers a final act of violence. With its energy production suddenly cut off, the star can no longer support the crushing weight of its outer layers. In a fraction of a second, the core collapses under gravity. Protons and electrons are forced together into neutrons, and the core becomes an ultra-dense neutron star, or in some cases, it continues collapsing into a black hole. The infalling outer layers slam into this hard core and rebound, and an enormously powerful shockwave rips outward through the star. The star is torn apart in a supernova explosion. In that brilliant, brief flash, the star unleashes more energy than billions of normal stars combined. For a few weeks, this single stellar death can outshine a whole galaxy of ordinary stars. Temperatures and pressures skyrocket so high that elements heavier than iron are forged in the fury. Gold, silver, iodine, uranium, all the rare atoms heavier than iron that exist in nature, can be synthesized in these final, fleeting moments via rapid neutron bombardment. The supernova then scatters the star's contents, both the newly minted heavy elements and all the elements it fused over its lifetime, into space. It is a cosmic seed spreading. The ashes of dead stars, carbon, oxygen, nitrogen, iron, calcium, and more, mix into the diffuse gas of the galaxy. There are other cosmic forges as well. When 2 neutron stars, the ultra-dense remnants of supernova cores, spiral together and merge, they create an even more exotic alchemy. The collision triggers a kilonova explosion where torrents of neutrons slam into atomic nuclei to build some of the heaviest elements in the periodic table. Such events are rarer than ordinary supernovae, but they are prolific producers of elements like gold, platinum, and rare earth metals. The gold in a wedding ring, or the platinum in electronics, likely came from one of these spectacular mergers in our galaxy's past. Over time, generation after generation of stars enriches the cosmos. The first stars contained almost nothing but hydrogen and helium. When they died as supernovae, they seeded their surroundings with heavier elements. New stars formed from those enriched gases, incorporating the heavy elements into their makeup. Each subsequent generation had a bit more of the periodic table to work with. By the time our Sun and its planets formed, about 9 billion years after the Big Bang, the gas cloud that birthed them was laced with the debris of countless earlier stars. That is why Earth has an iron core and a crust rich in silicon and oxygen. It's why our bodies have carbon, nitrogen, calcium, and phosphorus. All those atoms were fused in stars or created in star deaths, then scattered into space, then gathered into new star systems like ours. In this way, stars are the mothers of the elements, the artisans crafting the raw materials for planets and life. Not all stars die in explosions. Smaller stars, up to a few times the Sun's mass, live more quiet lives and die more gently. A Sun-like star, after fusing hydrogen into helium for billions of years, eventually swells into a red giant, shedding its outer layers into space. The star's core, no longer sustained by fusion, shrinks into a hot white dwarf about the size of Earth. The cast-off outer layers drift away as a glowing planetary nebula, enriching the surrounding space with elements like carbon and nitrogen that were formed in the star's late stages. The white dwarf slowly cools over trillions of years. So even without a supernova, these stars return much of their substance to the galaxy and contribute to the chemical evolution. It's a cycle of cosmic reincarnation. Massive stars explode and seed nebulae with heavy atoms. Lower mass stars gently send off their envelopes of enriched gas, and in both cases, the ashes become part of the raw material for new stars and planets. In a sense, it's like a cosmic phoenix. From the ashes of old stars, new ones will one day be born. The periodic table, that chart of elements from hydrogen to uranium and beyond, is essentially a family tree of the cosmos. Hydrogen and helium, and a dash of lithium, are the ancient ones from the Big Bang. Lithium, beryllium, and boron are rarer. Most of them were formed later by cosmic rays shattering heavier atoms. Carbon through iron are primarily the handiwork of stars, steadily burning in their cores or in red giant stages. Elements heavier than iron come from the dramatic explosions of supernovae and the mergers of neutron stars. Each element has a story, a birthplace in some long-gone star or cosmic event. Scattered across space by stellar winds and violent blasts, these elements eventually coalesce into new worlds and perhaps new living beings. Every atom in your body has traversed this cycle. It has been part of a star or multiple stars before finding its way into you. The iron in your blood was forged in a massive star's core and liberated in a supernova before the sun existed. The calcium in your bones, the oxygen you breathe, products of stellar alchemy. We are truly made of star stuff. The universe began with only the lightest elements, and through the work of countless stars over billions of years, it now boasts a rich periodic table that enables planets, oceans, and life. The stars not only light up the universe, they also serve as crucibles, steadily enriching a once nearly pristine cosmos into one rich with chemistry. They turned a simple beginning into the complex reality we see today, giving birth to the elements of everything tangible around us. The rise of complexity, from atoms to life, from a nearly uniform haze of particles in the early eons. My evolution has been one of growing complexity. The simple has given rise to the intricate. Out of fundamental particles came atoms. Out of atoms came molecules. Out of molecules came stars and planets. And on at least one world, out of a mingling of molecules came something astonishing: life. The journey from inert matter to living cell is a tale of order emerging from chaos, of complexity born from simplicity. The building blocks for complexity were forged in stars and distributed by stellar explosions. In the aftermath of supernovae, clouds of gas laced with diverse elements cooled and condensed. In some places, these clouds formed new stars, surrounded by disks of leftover dust and gas. Within those disks, grains of dust stuck together, attracting more particles, growing into pebbles, then rocks, then mountain-sized chunks. These merged into planetesimals and eventually into planets. On at least one of these young planets, Earth, the conditions were just right for an even greater complexity to emerge. Earth formed roughly 4.5 billion years ago around our young sun, built from that enriched cosmic material. It started hot, molten, and hostile. But within a few 100 million years, it cooled enough for liquid water to pool on its surface. A thick atmosphere formed. Chemistry began its restless experiments. Simple molecules combined into larger, more complex ones. Carbon, with its versatile bonding, formed diverse organic compounds. In warm little ponds or deep-sea hydrothermal vents, aided by lightning or geothermal heat, some molecular arrangements showed a remarkable property. They could make rough copies of themselves. By a process still not fully understood, mere chemistry gave rise to biology. Perhaps membranes formed naturally, creating tiny droplets where reactions could concentrate. Perhaps catalytic molecules like RNA both carried information and facilitated their own replication. Somehow, somewhere in those primordial waters, the first living cells sparked into existence. Life is a profound leap in complexity, a tiny island of order amid a broader sea of entropy. But it doesn't violate the second law of thermodynamics. It locally decreases entropy by feeding on energy and expelling waste heat, increasing entropy in its surroundings. In doing so, life carves out niches of organization. A cell takes in sunlight or chemical fuel and uses that energy to build intricate molecules, to move, to reproduce. Plants on early Earth learned to harness sunlight to build sugars, photosynthesis, introducing oxygen into the atmosphere and transforming the planet's chemistry. Life's emergence may have been a gradual increase in complexity, from simple replicating molecules to encapsulated protocells to true cells with metabolisms. With replication came mutation and natural selection, and thus evolution began its creative exploration of forms. Over billions of years, on that one known fertile world, and perhaps on others we have yet to find, simple life branched into a stunning diversity. Single-celled organisms in the seas evolved into more complex cells with nuclei. Some of those joined together in cooperative colonies, eventually giving rise to multicellular organisms. By 600 million years ago on Earth, the oceans teemed with simple animals. Life gradually conquered land. Plants and fungi were followed by insects, amphibians, reptiles, mammals, birds, each filling new ecological roles. Coral reefs, rainforests, and savannas became tapestries of interacting species, an intricate web of life, analogous to the cosmic web of galaxies, each organism playing a part in a larger whole. Even apart from life, the universe generates complexity. When water freezes into snowflakes, it forms delicate six-fold symmetric crystals. When air flows over a wing, it can create organized vortices. When chemicals react, they sometimes spontaneously form patterns like swirling convection cells. These are inanimate examples of order arising naturally from underlying laws. Life takes this self-organization to another level. It not only creates order, it sustains it and builds upon it, evolving greater complexity over time. With life, the universe developed new properties. Living things can grow and heal. They can adapt to changes. They can collect information about their environment and respond. And with the emergence of nervous systems, particularly brains, the universe took a critical step further. It began to perceive and to feel. Senses arose, eyes that capture light, ears that capture sound vibrations, tongues to taste chemical nuances. Simple creatures might just respond reflexively, but as evolution progressed, more sophisticated awareness emerged. By the time mammals and other advanced animals arrived, the universe had achieved something profoundly new. It could experience its own beauty and terror through conscious minds. On Earth, this crescendo of complexity ultimately produced beings who could look up and wonder at the stars. Tiny conscious minds, arisen from cosmic dust, Now contemplate cosmic dust. The line from the primordial quark-gluon plasma to a human brain is not a straight one, but it's unbroken. Each step followed the laws of physics and chemistry, building layer upon layer of emergent complexity. It took 13.8 billion years of cosmic evolution to turn simple hydrogen into eyes that can see and minds that can understand. And we are the result. It is perhaps the greatest marvel. The universe started as a near-uniform soup of particles, and through the interplay of fundamental forces, it has become aware in parts of itself. Order from chaos, simplicity to complexity, that trajectory has defined my history. Given the right conditions and enough time, matter and energy organized into patterns of increasing sophistication. Galaxies, stars, planets, life, mind. Each is an example of the cosmos transcending itself, finding new ways to be. Galaxies, cosmic ecosystems and evolution. Galaxies themselves are not static backdrops. They have life cycles and evolutions of their own. In the early eons, galaxies were smaller and often irregular, frequently colliding and merging. Through gravity's mergers, many little proto-galaxies assembled into the grand galaxies we see today. A spiral galaxy like the Milky Way likely began as several smaller clumps that coalesced, their stars and gas settling into a rotating disk over time. Each collision or close pass between proto-galaxies reshaped them, sometimes igniting furious bursts of star formation, sometimes turning chaotic swarms into more orderly forms. In their youth, galaxies tend to be rich in gas and dust, actively forming new stars. Brilliant nebulae, stellar nurseries, glow in their spiral arms. Clusters of massive blue stars sparkle throughout their disks. It's akin to a city in the throes of growth, vibrant and bustling with newborn stars. Galaxies in this stage can shine extremely bright, especially if their central black hole is feeding. At the heart of virtually every sizable galaxy lies a supermassive black hole, millions or billions of times the mass of the Sun. When ample gas falls towards such a black hole, it forms a hot accretion disk and jets that blaze as a quasar, outshining the entire galaxy. In the young universe, quasars were common, making some galaxies spectacularly luminous. They also acted as cosmic feedback engines. The energy and winds they blasted out could heat and push away gas, regulating or even temporarily quenching star formation in their host galaxies. Thus, a galaxy's central black hole, though tiny compared to the whole galaxy, can exert an outsized influence, sometimes playing the role of both nurturer and destroyer, triggering starbursts with shockwaves on one hand, or starving the galaxy of gas on the other. As galaxies mature, they often lose or use up much of their gas. Star formation slows down. A spiral galaxy might burn through its interstellar gas or have it stripped away, especially if it resides in a cluster where interactions with hot intracluster plasma can sweep gas out. The once blue spiral may then fade to a yellow-white hue dominated by middle-aged stars, or if it merges with others, it may transform into an elliptical galaxy, a spheroidal, more randomized collection of stars with little cold gas left. These red and dead galaxies shine with the blended light of billions of old, reddish stars and host very few new stars. They are like cosmic cities that have grown and transitioned into a quieter retirement, with only the glimmers of streetlights, the aging stars, left at night. Yet even in apparent retirement, galaxies are not truly inactive. Stars within them continue to evolve and die, enriching the galaxy with each generation. Occasionally, a galaxy can rejuvenate if fresh gas is acquired, say by accreting a gas cloud or a small gas-rich galaxy. New stars may flare to life again. And when galaxies merge, the influx of new material often triggers vigorous star formation, lighting up the merger remnant for a time, so a dead galaxy can flicker back to life under the right circumstances. On cosmic timescales, Galaxies undergo cycles of formation and transformation. They accrete gas from intergalactic space along filaments, fueling new stars. They interact and merge with neighbors, growing larger or changing shape. Massive galaxies act as predators, tidally shredding and absorbing smaller dwarf galaxies that venture too close. Indeed, our Milky Way is in the process of cannibalizing several dwarf companions, their stars strewn in streams across our sky. Meanwhile, within each galaxy, stars continue the cycle of birth and death, slowly altering the galaxy's makeup. The abundance of heavy elements increases with each generation of stars, enriching the galaxy's gas and the next generation of solar systems. Galaxies can be thought of as cosmic ecosystems. Some are bustling and gas-rich, spiral arms full of blue O-type stars and pink hydrogen clouds. Others are old and quiescent, ellipticals glowing softly with red giants. They live in environments, some in isolation, others in dense clusters. And these environments shape them. In a crowded cluster, a galaxy's gas can be stripped by ram pressure as it moves through the cluster's hot medium, quenching its star formation. Or a close encounter with a neighbor can trigger a fireworks show of new stars. Environment and internal dynamics together drive a galaxy's evolution. Our own Milky Way is a fairly typical large galaxy, midway through its life. It still forms new stars, a few per year, though it's past its youthful peak of star formation. It has an active center with a dormant black hole that flared as a quasar in the distant past, but is quiet now. In about 4 to 5 billion years, the Milky Way will merge with the Andromeda Galaxy. Over another few billion years after that, they will likely form a large elliptical galaxy, dubbed Milkomeda by some, with most of the gas consumed or ejected. By then, star formation will slow dramatically in our region of the universe. This is the long future for many galaxies, to merge into larger entities and gradually run out of the cold gas needed to make new stars. In the fullness of time, the universe's galactic population will look different. Many current galaxies will have coalesced into giant ellipticals. Star formation will languish as the fuel is exhausted or locked in stellar remnants. But that is billions of years ahead. At the current epoch, the universe showcases galaxies in every stage, from newborn proto-galaxies in the distant young universe, as seen by our telescopes looking back in time, to mature spirals like the Milky Way, to ancient ellipticals in clusters that formed shortly after the Big Bang and have not had new stars in billions of years. Each galaxy is a chapter in my story, with a birth, a transformative adolescence, and a quieter maturity. Their evolution paints a dynamic picture, a cosmos in constant motion and change, where even the largest structures have life cycles measured in eons. Observable limits, the cosmic horizon. No matter how powerful our telescopes become, there is a fundamental limit to how much of me can be observed. We are bound by the speed of light and the finite age of the universe. Light, and any information, has traveled at most 13.8 billion years to reach us since the Big Bang. During that time, space itself has been stretching, so the farthest regions we can see are now much more distant than 13.8 billion light-years, currently about 46 billion light-years away. This defines our observable universe, a spherical bubble centered on the observer, wherever that observer may be, inside which light has had time to reach them. Anything beyond that sphere lies over the cosmic horizon, forever out of reach, not because it doesn't exist, but because its light will never have the chance to catch up to the ever-expanding space between. I often liken this to being in the middle of a vast ocean. You see a horizon around you, but you suspect the ocean continues beyond it. Likewise, beyond the edge of our observable universe, more universe likely exists, perhaps an endless expanse. The universe could be far larger than the portion we can see, possibly even infinite in extent. If space is indeed infinite, or at least so huge that it might as well be, then our observable sphere is just one patch in an endless cosmic quilt. There may be countless galaxies beyond our horizon, receding from us faster than light due to the expansion, their glow forever unreachable. We have not observed any edge or boundary to space. Wherever we point our instruments, we see galaxies or the afterglow of the Big Bang in the background. The simplest assumption is that what we see is a representative sample, and beyond our horizon, more of the same continues. The cosmic microwave background comes to us uniformly from all directions, supporting the idea that beyond our observable limit, conditions are similar. To the best of our knowledge, space just continues, likely with more galaxies, more voids, more everything, indefinitely, or until perhaps it curves back on itself. But if so, the curvature is so slight that any such loop would be far beyond our sight. The concept of infinity is both awe-inspiring and unsettling. If space goes on forever, then somewhere out there, far beyond what we can observe, every possibility might occur. Given infinite rolls of the cosmic dice, there could be regions where matter is arranged very differently, and perhaps even, by sheer chance, regions almost identical to our own observable universe. It's a strange thought. If the universe is infinite, then there are infinitely many observable universe-sized patches out there. Statistically, those patches could include ones with galaxies arranged exactly like ours, or even doppelgangers of solar systems, just by random distribution of matter. This isn't science fiction so much as mathematics, an implication of infinite volume. However, it's likely we can never verify this directly, as no information from those distant hypothetical realms will ever reach us. It remains a curious implication of an infinite cosmos. The observable universe itself is enormous, roughly 93 billion light-years in diameter at present, containing perhaps 2 trillion galaxies by some estimates. And it is expanding. Our horizon grows as time goes on, bringing new regions into view that were previously just beyond reach. In principle, given enough time, we could observe galaxies that are now slightly beyond our horizon as their light finally arrives. However, the accelerated expansion caused by dark energy complicates this. There is a future limit. Eventually, distant galaxies will recede so fast and so far that their light can no longer ever reach us, no matter how long we wait. In fact, many of the galaxies we can see now will, in the far future, fade away beyond a new horizon. We live in a fortunate time when we can still see deep into the cosmos. Countless eons from now, an observer in our location would see only the gravitationally bound remnants of the local group. The rest of the universe's galaxies would have slipped out of view. So there are really 2 horizons to consider. One in space, the current observable limit, and one in time, the eventual limit of what we will ever be able to observe, even if we wait forever. Both remind us of a humbling truth. We are not privy to the whole story, only our local chapter of it. The vast reaches beyond our sight could hold wonders we will never behold, perhaps variations of the structures we see, or perhaps domains with different physics entirely, but they are, in practice, outside our observable reality. Is the universe infinite, or just extremely large? Current observations, like measurements of the CMB's curvature, suggest space is extremely flat on large scales, which implies that if it is curved into a closed shape, the curvature radius is far larger than the observable universe. It might wrap around on itself like a 4D hypersphere, but if so, we see no repetition yet. We've looked for patterns, like seeing the same galaxy or same CMB hotspot in opposite directions, a telltale of a small universe where light has gone around and returned, but none have been found. So the universe's extent is at least many times larger than what we can see and possibly truly infinite. Standing on the cosmic shore of what we can observe, we peer out as far as the light allows, aware that an ocean of further reality likely lies beyond. This realization both humbles and excites. It humbles us because it underscores our limits. No matter how clever we become, Some parts of existence will remain hidden by distance or time. It excites us because it suggests the cosmos may be even grander than we know, an ever-expanding frontier for our imagination. We are like sailors who have mapped a tiny region of a vast archipelago. We suspect there are countless islands beyond the mist, even if we may never visit them. The observable universe is our cosmic horizon, but not the universe in total. That distinction is a key part of the cosmic perspective. The multiverse. Beyond our universe. Is our universe the only one, or just one bubble in a much larger froth of universes? This question stretches our concepts of reality and edges into speculation. Yet modern cosmology allows for the possibility of a multiverse, multiple universes coexisting, perhaps each with different properties, and possibly forever inaccessible to one another. One idea arises naturally from eternal inflation theory. Recall that brief epoch of inflation right after the Big Bang, space expanding at breakneck speed. Inflation might not have been a one-off event that happened uniformly everywhere. Instead, it could be an ongoing process in a larger space-time. In this picture, our universe's Big Bang was just one patch where inflation ended or slowed and dropped its energy into creating matter and radiation. Elsewhere, inflation might continue, exponentially expanding space and occasionally sprouting new bubble universes like foam on boiling water. Each bubble is a Big Bang of its own, an expanding universe with potentially its own laws of physics or constants of nature. We happen to live in one such bubble. Beyond it, other bubbles may be born and grow, but they are separated from us by inflating space that rushes them away faster than any signal could bridge. If this model is correct, and it's speculative but grounded in some plausible physics, the wider reality would be an ever-growing multiverse. Each bubble universe could have different conditions. Perhaps in one, the proton is a bit heavier, or gravity a bit stronger. Maybe some are sterile, collapsing quickly or never forming galaxies, while others might be even more hospitable to life than ours. If there is a multitude of universes with varying properties, it could even explain why our universe seems so well suited for complexity and life, the so-called fine-tuning problem. We observe this universe because only in rare Goldilocks universes like ours do observers arise. In the countless other universes that are inhospitable, no one is around to notice. This multiverse of bubble universes is a heady concept. These other universes are not located in our space. They don't exist over there beyond our observable universe. Rather, they are separate spacetimes entirely, outside of our bubble's bounds. We cannot travel to them or communicate with them. The laws of physics within each bubble dictate that nothing can escape one universe to visit another. They even searched the cosmic microwave background for hints of collisions with other bubbles, which might appear as subtle circular patterns in the sky's temperature map, but so far have seen nothing clearly indicating such an event. It may be that our bubble never collided with another, or if it did, the signs are too faint to discern. There are other multiverse notions too. Some come from quantum mechanics and the idea of many worlds. Every quantum measurement could cause reality to branch into multiple outcomes. In that interpretation, all possible outcomes of every event do occur, each in its own branch of the wave function, a vast proliferation of parallel universes where history plays out differently each time. In one branch, a quantum coin lands heads. In another, tails. In one, a certain galaxy forms planets with life. In another, the same gas cloud might not fragment into planets at all. These many worlds universes are less like bubbles. They occupy the same space, but in separate quantum branches, and more like parallel dimensions layered on top of each other, non-interacting. If that is a true picture of reality, then even as we speak, countless new universes split off, and the total multiverse becomes an ever-branching cosmic tree of possibilities. But again, these branches are inaccessible to each other. Once split, they cannot communicate or merge. These concepts are at the frontier of speculation. By definition, other universes, whether separated by continual inflation or quantum decoherence, would be disconnected from our own. No telescope can peer into them. No signal can be exchanged across such a divide. We look for indirect hints, like the possible bubble collision imprint or subtle effects in fundamental constants. But so far, there is no conclusive evidence that other universes exist. For now, the multiverse remains an intriguing idea, suggested by certain theories and mathematical extrapolations. If true, it means that my story, everything from the Big Bang to now, is just one volume in an infinitely larger library. The word universe itself would need redefining, coming to mean not everything that exists, but rather one constituent reality among many. The cosmos of cosmos, where universes are born like sparks in a fire, where even nothingness might give birth to new existence unpredictably. As the universe personified, I too wonder, am I alone, or one of countless siblings in a grand cosmic family? It's a question we may never empirically answer, but the very possibility expands our sense of what existence could be. It reminds us that reality might have levels beyond this one, and that our universe, immense as it is, could be a small part of an even vaster multiverse. Fate, the long future, entropy, and the big freeze. All things that have a beginning also have an end, it seems. And so it will be with me, unless unknown new physics intervenes. What does the far future hold? As I continue to expand under the influence of dark energy, I appear destined for a slow and quiet fade rather than a sudden cataclysm. This is the path of the big freeze, the heat death of the universe, where entropy reaches a maximum and meaningful change grinds to a halt. Trillions of years from now, the era of starlight will draw to a close. The galaxies, currently bustling with star formation, will exhaust their supplies of gas. No new stars will be born once the fuel runs out. One by one, existing stars will age and die. Massive blue stars last only millions of years. Sun-like stars burn out over billions. Even the small red dwarfs, which sip their fuel so slowly they can live trillions of years, will eventually use up their hydrogen. In the far future, red dwarf stars, those dim, long-lived embers, will be the last shining points in galaxies. But eventually, they too will wink out. As the stellar fires go out, the universe will be lit only by the ghostly afterglow of stellar remnants. White dwarfs, the cooling cores of dead medium stars, will provide a faint glow as they radiate away their remaining heat over quadrillions of years. Neutron stars will spin down and darken. Black holes will lurk invisibly. The once bright galaxies will be populated only by these remnants of stars. White dwarfs, neutron stars, black holes, and diffuse gas, much of it likely swept out of galaxies or fallen into holes. Imagine a far future astronomer living on a surviving world orbiting a cool red dwarf star, trillions of years from now. The night sky that this distant descendant would see is profoundly different from the one we behold today. Looking up, they might find no Milky Way band arching overhead. Our galaxy's stars long since faded or merged into a featureless mass. Andromeda, once a great galaxy in our sky, would have long ago merged with the Milky Way into a bloated elliptical, but even that would be dark, its remaining stars too faint to see at intergalactic distances. In fact, beyond the boundaries of their home galaxy, an observer might see nothing at all. The accelerating expansion will have driven all other galaxies beyond the horizon. The universe would seem empty and static to them. Unaware of the rich past when galaxies filled the heavens, they might deduce the presence of an accelerating expansion from local motions of gravitationally bound objects. But they would not see the cosmic microwave background. It would be undetectably cold, or any galaxies beyond their own. The cosmos would look like a dark, endless void, punctuated only by the dim glow of a few nearby stellar embers. The dramatic youth and bustling middle age of the universe would be hidden by the veil of time. As eons pass in this far future, even black holes, the last bastions of something substantial, will not last forever. Through Hawking radiation, black holes slowly evaporate, emitting faint particles over incomprehensible timescales. For a stellar mass black hole, this takes 10,067 years or so. For the supermassive black holes weighing billions of suns, the evaporation time is enormously longer, on the order of 100 years or more, a number with 100 zeros. But given a truly vast expanse of time, even these giants will evaporate to nothing, one by one. They will end not with a bang, but with a faint hiss of particles and photons, leaving behind a space that, apart from those particles, is empty. What remains then is essentially a thin gruel of particles and radiation, spread ever more thinly by expansion. If protons are unstable, some theories predict they might decay after 10 to 34 years or more. Then eventually even matter as we know it will disintegrate into radiation and elementary particles. If protons are stable, matter will still erode via other processes. Nuclear reactions in white dwarfs, so-called proton tunneling, might convert them to iron over 10,000–1500 years, or extreme gravitational events might occasionally cause matter to annihilate. But regardless, without any energy sources to concentrate or use energy, everything just drifts. The temperature of the universe, which has been dropping since the Big Bang, will asymptotically approach absolute zero. The cosmic microwave background, now 2.7 K, will continue to redshift to ridiculously long wavelengths and low energies, essentially fading entirely from existence. All structures that are not gravitationally bound will be carried away from each other by expansion, but eventually, even expansion will slow from our perspective, because we won't see anything moving. It will all be beyond our horizon. This final state is often called heat death. It's a state of maximum entropy, where nothing useful can happen, because all energy is uniformly distributed. In a sense, time itself loses meaning in such a state because time is marked by change, and in heat death, effectively, nothing changes. It is an ending that comes not with a bang, but with a whimper, an ever-fading whisper of what once was, as the universe grows quiet and cold. This vision of the end is melancholic but also serene. A universe that begins in fire ends in stillness. There are, however, other hypothetical endings that depend on dark energy's nature. If dark energy were to become unstable or grow stronger, it could culminate in a big rip, where the repulsive force becomes so strong that it tears apart galaxy clusters, then galaxies, then solar systems, and ultimately atoms themselves in a final, catastrophic stretching of space-time. Conversely, if dark energy somehow reversed, or a new attraction emerged, the expansion could halt and reverse, leading to a big crunch, the universe recollapsing into a hot, dense state, perhaps to rebound in a new Big Bang in cyclic fashion. These scenarios seem unlikely given current data, but they remind us that our knowledge is not absolute. For now, the Big Freeze is the fate that best fits what we observe. And yet, one might wonder, is that truly the end? Some have imagined that, given infinite time, random quantum fluctuations in an empty void might spontaneously create new ordered regions, a kind of Boltzmann brain scenario, or even a new Big Bang in isolated patches. Others speculate that the universe might tunnel into a lower energy vacuum state, a possibility in some particle physics models, which would trigger a bubble of true vacuum expanding at near light speed, a cosmic reboot that would destroy our universe as we know it and create new conditions. This is known as vacuum decay. Such events are speculative and exceedingly improbable on any timescale we can fathom. They lurk as wildcards in the far future. Barring those, the picture of an ever-expanding, cooling universe stands. From the blazing hot spark I once was, I will have become an expanse so vast and so cold that even the faint afterglow of my birth the cosmic microwave background, will have redshifted into obscurity, its wavelengths stretched so much that it is effectively undetectable. All memory of the vibrant eras, when galaxies shone and life thrived, will be imprinted only in the distribution of dead matter and radiation, if at all. Time, in a sense, will have nearly stopped, because nothing happens from one eon to the next. It is a contemplative end state, a cosmos that simply is, in final equilibrium, with no arrow of time. However, the journey to that end is staggeringly long, and we, living in the universe's youth, have essentially all of cosmic history ahead of us before that fate plays out. Stars still have trillions of years to shine. Planetary and perhaps biological evolution on surviving worlds could continue in ways we can't imagine. The end will not come for an absurdly, almost meaninglessly distant future. For now, the universe is vibrant and ongoing. And in any case, the end in heat death would be so gradual as to be experienced less as an abrupt doom and more as a slow, ever-fading twilight. Information. The universe. As code. Beneath the atoms and the forces, beneath the stars and galaxies, there is an abstract layer to reality. The layer of information and mathematics. It is often said that mathematics is the language of the universe. Indeed, the laws that govern my behavior can be written as equations, sometimes simple, sometimes exceedingly complex, but always mathematical. Why should a falling apple follow a precise formula? Why should planets trace ellipses or light waves obey elegant equations? It is as if a code runs under the surface, a set of rules and relationships that everything, from quarks to galaxies, must follow. This realization has led some thinkers to wonder whether the universe is fundamentally made of math, in the way that a poem is made of words or a symphony is made of notes. From one perspective, the physical world can be seen as information. A particle in a particular state carries information, its position, momentum, spin, etc. When particles interact, they are essentially performing computations according to the laws of physics, updating that information. Conservation laws, like those of energy or electric charge, are like cosmic accounting rules, ensuring that as processes occur, certain quantities remain consistent. Even black holes, once thought to destroy everything that falls in, seem to retain, in encrypted form, the information about what they swallow, so that information is not truly lost to the universe, lest quantum physics be violated. This is the essence of the black hole information paradox and its presumed resolution. Information, like energy, is conserved. Think of the universe as a vast computer, not made of silicon chips, but of fields and particles, performing trillions of operations every moment. The initial conditions of the Big Bang, combined with the algorithms of nature, the laws of physics, have led to the output we see now: galaxies, stars, life, and us. What's astonishing is that these laws are often expressible in concise mathematical terms. A few simple equations can describe a pendulum's swing, a planet's orbit, or the propagation of a light wave. Out of relatively simple rules, immense complexity can emerge, just as a simple fractal formula can generate an endlessly intricate pattern. The Mandelbrot set, for example, comes from iterating a basic complex equation, yet yields infinite complexity and beauty in its visual form. Likewise, the universe's fundamental equations, whether it's general relativity and the standard model of particle physics, or a deeper theory we haven't discovered yet, give rise to the fractal-like richness of the cosmos. Some scientists and philosophers take this idea further, suggesting that the universe is a kind of simulation or hologram. If the laws of physics are akin to code, one could imagine they are being run on some underlying reality. The simulation hypothesis muses that perhaps an advanced intelligence or a natural higher-order structure could set up a universe with certain rules and let it play out, much like a computer simulation. This idea remains firmly in the realm of speculation, There is no evidence we are in a simulation, but it underscores how rule-based the cosmos is. Whether or not deliberate, the universe behaves like a system following a set of algorithms. Every supernova explosion, every leaf growing, every electron transition follows specific laws. Another perspective is that mathematics isn't just the language of the universe, but the substance of it. In this view, the mathematical universe hypothesis, the physical world is a mathematical structure. We don't invent mathematical truths, we discover them because the universe itself adheres to them. It's as though each particle is a bit of code executing, and each physical law is a subroutine in the grand cosmic program. When we do physics, we are reverse engineering this code. We find that the same mathematics that describes the curve of a ball can describe the orbit of a moon. The same differential equations govern electrical circuits and nerve impulses and vibrating strings. Such unity hints that diverse phenomena are unified by underlying principles, like a software that can produce many different outputs from the same basic instructions. On a deep level, one can say that information is the bedrock of reality. The specific arrangement of matter and energy is an arrangement of information. DNA, for example, is molecular information encoding the structure of a living being. A star's light carries information about its temperature and composition. The pattern of galaxies in the cosmic web encodes information about the primordial fluctuations and the content of the universe, like how much dark matter and dark energy it has. In the distant future, when entropy is maximized, information will be spread thin and chaotic, effectively lost to any reconstructive use, meaning the record of what transpired will have been erased. But right now, we live in an epoch rich with information. Stars and planets and living minds are pockets where information is concentrated, processed, and sometimes communicated. Modern theoretical physics has even proposed something called the holographic principle, the idea that all the information contained in a volume of space can be represented as information on the boundary of that region, analogous to how a hologram encodes a 3D image on a 2D surface. In such a case, our three-dimensional universe might fundamentally be a kind of projection of data encoded on a distant 2D surface, an astounding concept suggesting that geometry and gravity emerge from more abstract information-based laws. This principle, born from studies of black hole thermodynamics, reinforces the notion that information is central to how reality works. So, is the universe a code, and math its source? In a poetic sense, yes. The deeper we delve, the more we find that at its heart lies an elegant order described by numbers and logic. Galaxies follow the equations of gravity, electrons dance to the quantized rhythms of quantum mechanics. It's as though a great book is written in the language of mathematics, and we, as conscious parts of the universe, have learned to read some of its chapters. Through this lens, one can see the universe as a grand information structure or a cosmic algorithm unfolding over time. When we gaze at the night sky and discern patterns, when we use equations to predict an eclipse or the behavior of a new particle, we are tapping into this underlying order. Perhaps when we do mathematics, we resonate with the deepest fabric of reality itself. We are the universe contemplating its own code. Earth and humanity. A fragile world of thinkers. Amidst the vastness of space and the immensity of cosmic time, there exists a small rocky planet orbiting an unremarkable star in the outer regions of a typical galaxy. By cosmic standards, the planet is insignificant, a speck of dust in a sunbeam, a single pixel in the grand picture. Yet this planet, Earth, is indescribably precious, for it is a cradle of life and of mind. It wears a delicate veil of atmosphere, a thin blue film encasing it, protecting and nurturing the life below. Under that blanket of air, liquid water flows and clouds float, a rarity in our solar system and perhaps in the galaxy. In this nurturing embrace, life has flourished for over 3.5 billion years. Single-celled organisms transformed Earth's oceans and skies, and eventually complex life exploded in diversity. Lush green forests, sweeping savannas, deep blue oceans, all are manifestations of cosmic ingredients come alive. From space, Earth is a serene blue marble, swirled with white clouds and brown-green lands, a gem against the blackness. But this beauty is fragile. A slight change in the atmosphere's balance, a wayward asteroid impact, or the careless actions of its own inhabitants could upset the precious equilibrium that has persisted for eons. Earth is our oasis in a vast desert. As far as we know, it is the only place where the universe blooms into life and consciousness. On this world, the universe has done something extraordinary. It has become aware of itself through us. Humans, one of countless species on Earth, possess the remarkable gift of curiosity and intellect. We are thinkers and dreamers, capable of gazing at the night sky and contemplating our origins. Out of the same carbon, oxygen, and nitrogen that were forged in ancient stars, Earth has produced beings that can study stars. Tiny, self-aware collections of atoms now question the very cosmos that made them. We formulate equations to capture the mechanics of galaxies and the minutiae of atoms. We create art and music inspired by the cosmos's grandeur. We have built eyes, telescopes, that peer deep into space and far back in time, and ears, radio dishes, that listen for whispers from the stars. We have even sent messengers, robotic probes like Voyager, beyond our planetary neighborhood, carrying greetings to whatever might be out there. Humanity's presence is but a blink in cosmic time, mere moments compared to the age of the universe. Yet in that blink, we have begun to unravel many cosmic mysteries. We have discerned the age of the universe, the process by which stars shine, the way continents drift on our planet, and the code of DNA that underlies life. We've learned to harness fire, then electricity, then the nuclear energy once only found in stars. In a short time, we have become powerful enough to alter our own planet, changing the composition of the atmosphere, warming the climate, shifting the course of rivers and the fate of species. This power brings responsibility. We can either be wise caretakers of our fragile world or unwitting agents of its destruction. The awareness of our own impact is itself a byproduct of the universe becoming conscious. We are the first species that we know of to understand extinction, to comprehend the greenhouse effect, to deliberately take steps to protect other species and our environment. In us, the universe is trying to preserve its own delicate cradle. Yet despite all our knowledge, we remain small. Our entire world is a mote of dust suspended in a sunbeam, as one famous observer described upon seeing Earth from billions of miles away. In 1990, when a spacecraft took a distant photo of Earth, the pale blue dot image, it revealed our home as a tiny pixel of light in the vastness of space. Every human who ever lived, every dream, every war, and every act of love played out on that imperceptible dot. Such a perspective underscores both our insignificance in physical terms and the profound singularity of our situation. It should instill humility, reminding us that petty divisions and quarrels mean nothing against the backdrop of the cosmos. It should also instill unity, highlighting that we all share this one fragile world. Earth is our home, and at least for now, our only home. Even our own sun, now middle-aged at about 4.6 billion years old, will swell into a red giant in several billion years, likely consuming Earth or at least rendering it uninhabitable, before shedding its outer layers and ending up as a white dwarf. Earth's habitability is transient on geological timescales, another reason humanity's awareness and foresight are important. Our planet sits in a habitable zone by fortunate circumstance, shielded by a big brother, Jupiter, that deflects some comets and asteroids, endowed with a large moon that stabilizes its tilt and seasons. It's as if a series of cosmic coincidences set the stage for a stable environment where intelligent life could spark and flourish. Whether these circumstances exist elsewhere is still unknown, but we have begun to search among the exoplanets for other blue dots. We send out radio signals and listen for voices from the stars, not knowing if anyone is there. So far, the cosmic silence is profound, but our efforts have only begun. Each exoplanet discovered, and there are thousands now, is a reminder that our sun is just one of billions of stars that could host a living world. In nurturing life and giving rise to minds, Earth has enabled the universe to know itself. The thinkers and dreamers of our planet add a new layer of meaning to the cosmos. Through us, random matter has become self-aware, and the universe has gained the ability to reflect on its own existence. We look back in time with our telescopes and reconstruct the universe's history, essentially the universe looking at its baby pictures. We imagine possible futures, which is the universe contemplating its own destiny. In our science and art, the cosmos achieves self-expression and self-comprehension. Of course, we do not know if we are unique. Perhaps in some other galaxy, or even somewhere else in our own, other beings gaze at the stars and wonder as we do. If life is common, then the universe may be brimming with pockets of awareness, each distinct, yet each a facet of the cosmos awakening. If we are rare or even alone at the moment, then our responsibility is even greater, for we bear the sole torch of consciousness in a vast, dark space. In either case, at this moment, we know of only us on this pale blue dot, the universe aware of itself, the meaning of conscious life. It has been said that we are a way for the cosmos to know itself. This isn't just poetic fancy, it is quite literally true. The atoms that compose our bodies were forged in stellar furnaces. The energy that fuels our thoughts is sunlight captured by plants. We are children of the cosmos, made of its substance. And now we turn back to contemplate our origins. In us, the universe has eyes to see, and ears to hear, and a mind to reflect on it all. We are the universe made conscious, star stuff pondering the stars. Consider the arc. For billions of years, the universe unfolded without an observer. Stars lived and died, galaxies collided and formed, planets swirled, an epic drama with no audience, no commentary. But with the emergence of life, and eventually intelligent life, the universe gained the ability to witness itself. Through conscious beings, it can appreciate beauty, experience emotions, and seek understanding. When we marvel at a sunset or a spiral galaxy, it is the universe marveling at itself. When we feel awe, it is the cosmos reflecting on its own splendor. We, as conscious beings, ask, why are we here? What is all this for? These profound questions might not have definitive answers, but the act of asking them is itself remarkable. It means the universe has reached a state where it can question its own existence. We build complex philosophies and religions. We create scientific theories and narratives, all attempts of the cosmos, via human minds, to make sense of itself. Perhaps meaning is not inherent out there in the equations. Perhaps it is something we create. But that creation of meaning by us is itself a cosmic process. When we peer through a telescope, it is the universe examining its distant past. For the light that reaches us left those galaxies millions or billions of years ago. When we split an atom to see what's inside, it is the universe probing its own substructure. When we send spacecraft to other worlds, it is the universe extending a part of itself to new realms. Our art, our music, our dreams are ways the universe reflects on different aspects of reality: emotional, aesthetic, imaginative. Even our conflicts and struggles can be seen as the universe wrestling with itself, trying to know itself in different ways, though we strive for the higher harmony rather than conflict. This perspective carries a certain responsibility. If we are the universe become conscious, then our actions are an expression of the cosmos. How we treat our planet and each other is how the universe, through us, treats itself. The fragile Earth is the only vessel of the universe's self-awareness that we know. Thus, caring for Earth and for life is, in a sense, the universe preserving its chance to know itself. To squander our planet's riches or to extinguish ourselves in warfare would be, one could say, the universe stifling its own song. We often feel small and insignificant, and indeed, in terms of size, we are. But significance isn't solely a matter of physical scale. It's also about insight and awareness. A galaxy is magnificent, but it cannot contemplate its magnificence. A star cluster is bright, but blind. Yet here on this tiny world, matter has organized itself finely enough to achieve contemplation, to feel wonder, to value the experience of the cosmos. In that sense, a human being, or any conscious being, is a precious and astonishing thing, the universe looking back on itself and finding meaning. Are we alone in this cosmic self-awareness? We do not know. It's possible that intelligence blooms on many worlds, perhaps in different forms, following different senses and minds. If so, the universe has many eyes, many points of view gazing at it. If not, if we are a rarity or even unique at this moment, then we carry an important flame. In either case, as of now, we only have confirmation of our own awareness. Thus, each of us is a tiny piece of the universe that can reflect and marvel. That perspective can transform how we see ourselves. We are not apart from the universe. We are a part of it deeply and intimately. We are not strangers in it. We arose from it. The very brain with which you contemplate the cosmos is a product of cosmic evolution. When you feel the warmth of sunlight on your skin, that is a star's nuclear energy across 150 million kilometers of space, interacting with you, a moment of connection between your existence and the sun's. When you drink a glass of water, you are consuming molecules that may have been forged in interstellar space or in the early solar nebula. We are woven into the cosmic tapestry. This viewpoint can inspire a sense of purpose, or at least a perspective on purpose. Maybe the universe has no goal or intention. It simply unfolds according to physical laws. But through us, it has goals and intentions of a sort. Human goals, human intentions. We give the universe purpose, our purposes. If one believes there is a deeper spiritual purpose, one might say perhaps the universe's purpose was to give rise to awareness, to allow an avenue for understanding and love. Or if one sticks to a secular view, one can still appreciate that we create purpose locally. We imbue the universe with meaning by caring about what happens in it, by striving to know and to survive. Looking ahead, if we manage not only to survive but to thrive, humanity, or whatever we become in the future, be it enhanced humans or intelligent machines we create, or a fusion of both, may carry consciousness beyond Earth. We may spread life to other planets or artificial habitats, becoming a multi-world species. If that occurs, then the universe's self-awareness is extended and safeguarded. The cosmos will have eyes on many worlds, not just one. In a way, that could be considered the universe's way of making sure it will continue to be aware of itself despite local disasters. We often frame it as human survival and exploration, but from a cosmic perspective, it is also the expansion of the domain in which the universe feels and knows. One can imagine in the distant future, intelligent life, whether evolved from humans or completely alien, might network across star systems, exchanging knowledge. The universe might develop a kind of collective self-understanding, pieced together by many civilizations sharing their observations and thoughts. In that far future, the cosmos would be self-aware on a grander scale, not just isolated pockets of thinking beings, but a tapestry of many voices, perhaps creating a kind of cosmic mind spanning multiple star systems. This is speculative, but it's a beautiful vision. The universe awakening more fully as time goes on, rather than falling silent. And it may be necessary if life is to resist the slow creep of entropy. Only through knowledge, and possibly technology, might intelligence keep finding pockets of order and energy to sustain itself. Ultimately, whether consciousness remains an exceedingly rare flicker or spreads widely, the fundamental fact remains. We are made of the universe, and now we know that. We are the universe aware of itself. It is a revelation that carries both awe and a quiet sense of unity. In our hearts and minds, the cosmos has a home. Closing. The unfolding story. Now, at the end of this journey through space and time, let us return to the silence and darkness from which we began. Picture the void before the dawn of time, and then that first brilliant spark, the Big Bang, the universe's first breath. We began in silence, and for a long time there was darkness. In the distant future, a great silence may return as the stars fade. But here and now, between those deep darknesses, there is light and life. There is the sound of cosmic evolution, galaxies rotating, stars forming and exploding. In the vacuum of space, these make no sound, but in the grand scheme, one can imagine a kind of music of the spheres. And there is the sound of thought, our thoughts, giving voice to the cosmos. In the quiet that follows this telling, take a moment to feel your connection to the universe that surrounds you. Every atom in your body came from ancient events, explosions of stars, collisions of particles in the early universe, chemical alchemy in primordial seas. You are a child of supernovae and galaxies, shaped by 4.5 billion years of Earth's evolution. When you look at your hand, the carbon in it was made in red giant stars, the calcium in your bones in some long ago supernova, the iron in your blood in the core of a massive star. The universe is not distant or separate from us. It is literally within us. We are a way the cosmos experiences itself, as we have emphasized, and that means we carry its story within us. We have traveled from the Big Bang's fire to the present and gazed at the possible end. We've witnessed, in our mind's eye, the formation of atoms, the ignition of the first stars, the spinning up of galaxies, the coalescence of Earth, the rise of humans, and even the far, far future beyond human tenure. It's an immense story, one still in progress. The story of the cosmos is our story. It continues, even now, all around us. Galaxies, billions of light years away, are colliding and birthing quasars as we speak. New stars are being born today, in cloudy nebulae within our own Milky Way. On some planet, around one of those new stars, life may one day spark into being, adding another conscious voice to the cosmic chorus. Evolution on Earth carries on. We may become something greater or different in the future, or perhaps other species will rise if we fade. The cosmic expansion goes on, and with it time marches forward, carrying the story into new chapters. We stand, as human beings, at a unique moment. We have, for the first time, a pretty good grasp of our cosmic origins and context. We've deciphered messages in starlight that tell us how stars live and die. We've detected the faint echo of the Big Bang itself in the microwave sky. We've mapped galaxies and found the cosmic web. We've uncovered deep truths, that space and time are interwoven and dynamic, that matter is energy and energy matter, that black holes exist and gravitational waves ripple through space-time. We should feel profound gratitude or joy to be alive in this era of cosmic discovery. We should also feel a sense of stewardship, of carrying this precious knowledge forward and using it wisely. Imagine the future observers 1 million or 1 billion years hence, looking back at us, if records survive or if our actions echo through time. Will they remember us as the species who first awakened on this planet and reached for the stars? Will they see our era as pivotal when the universe first glimpsed itself? It's up to us, in part, what legacy we leave and whether we pass on this torch of awareness. Now, as we conclude, Return your mind to the quiet of the night sky. The lights dim in our mental planetarium, back to the darkness of space. Above you, the stars are wheeling slowly, as they have long before you were born, and will long after. But perhaps they look a little different now that you know their story. You can see in your mind's eye the invisible, the remnants of dead stars, the halo of dark matter, the stretching of space. You can almost feel the earth turning under you, carrying you eastward into the sunrise to come. The universe is not cold and alien. It is our home, our source, our larger body. We, its children, have read a few chapters of its grand story, and we hunger for more. We end not with an answer to every question, but with a reverent silence. In that silence, we recall the immensity of what we've witnessed. From the singularity to the infinite, from the first atoms to conscious minds, from simplicity to unimaginable complexity. It leaves us humbled, but also empowered with knowledge. The story of the universe is still unfolding. New pages turn every moment, and as long as there are minds to wonder and eyes to see, the universe will not be alone. Through our curiosity and our intellect, it will continue to know itself, to marvel at itself, and to tell its story. We are made of the universe, and it is still unfolding. In the beginning, there was darkness, a vast and silent expanse of cold gas and dust, adrift in the galactic night. For endless ages, nothing disturbed the quiet. The particles of ancient stars lay sparsely scattered, remnants of long-dead suns. Yet in that silence lived the potential for worlds and light. A gentle stirring began, perhaps the distant reverberation of a supernova's death cry, or the subtle pull of gravity drawing denser clumps together. The clouds started to swirl ever so slightly, an imperceptible dance born in stillness. Slowly, gravity tightened its grip. What was diffuse began to gather, whispering chaos into motion. At first, the movements were ponderous and slight, a drift inward here, a coalescing knot of dust there. But momentum grew. The great cloud, once tranquil and diffuse, began to collapse into itself. As it fell inward, it spun faster and faster, like an ice skater pulling in her arms. What had been a shapeless haze started to flatten into a broad disk, a whirling pancake of cosmic dust encircling an increasingly dense center. In that center, compression bred heat. Atoms pressed against atoms as the material piled in, and a hot, dense core formed, the seed of a star. Deeper and deeper, the young protostar collapsed under its own weight, temperature rising with each passing moment. The very nature of matter was changing. Gas became plasma, and hydrogen atoms, the simplest building blocks, were slammed together in an immense cosmic forge. Until at last, under crushing pressure and heat, hydrogen nuclei began to fuse into helium. In a sudden, radiant ignition, the protostar became a star. The darkness was broken by a newborn light. The sun had ignited at the heart of the collapsing cloud, and the solar system's story truly began. For the first time, our infant sun sent forth light and heat, a beacon in the void. It was not yet as steady as the elder star we know today. It burned with a ferocious, youthful energy, a T-Tauri sun throwing off violent winds. Those early solar winds blasted outward, sweeping the inner regions of the disk clear of the lightest gases and shaping the environment in which future planets would form. The new star's heartbeat, nuclear fusion in its core, created a magnetic field and an outward pressure that declared a new order in this once unremarkable patch of space. The sun's gravity now dominated, and all things would orbit around this central fire. But in those first moments after ignition, the sun was like a crying infant, brilliant, uncontained, and volatile. It sent a flood of particles and radiation washing over the surrounding disk. Yet despite this turbulent beginning, within the circling disk of gas and dust, smaller stories were about to unfold. Amid the sun's luminous new voice, the remaining material, the leftovers of starbirth, was not idle. It too continued to move and gather, heralding the emergence of new worlds. In the golden light of the young sun, countless dust grains began to stick together, first by the gentle static of their collisions, and then by gravity's growing pull. This was the dawn of the planets. Formation of the solar system. Encircling the sun was a vast rotating disk of debris, glowing gas and fine dust lit by the infant star's fire. Within this protoplanetary disk, chaos reigned and creation beckoned. Tiny motes of dust, no larger than powder, swirled in eddies and currents created by the disk's rotation. They collided softly, clumping into larger grains. Electrostatic forces, like a child's hair lifting toward a balloon, helped these particles adhere at first. Over thousands of years, grains became pebbles. Pebbles merged into rocks. In the dance around the sun, these rocks gathered into boulders and then into bigger chunks still. As the disk turned and thinned, regions of density emerged, pockets where material crowded together. In those regions, the clumps grew swiftly, their gravity pulling in more and more fragments as they cleared their paths. In a multitude of places, these growing bodies, planetesimals, were taking shape, the embryos of planets. They swept up dust in their vicinity like magnets. When they struck one another, sometimes they shattered in violent explosions, but more often they merged, becoming larger each time. The early solar system was a place of constant collisions, a shooting gallery of rock and ice. Every impact released energy, heating the young bodies and melting them inside if they were large enough, allowing heavy elements to sink inward and form cores, while lighter materials floated toward their surfaces. Closer to the nascent sun, only materials that could withstand fierce heat, metals and silicates, survived. Out of those solid ingredients, the inner planets were born. Farther out, beyond a certain distance, the sun's warmth waned and ices could remain solid. In those colder reaches, giants would emerge, capturing not just rock and metal, but also vast amounts of ice and gas. The disk was like a great plain of opportunity, with the sun's heat dividing it into realms. An inner realm of rock and iron, an outer realm of ice and gas. As time flowed on, dozens of protoplanets coalesced in the inner solar system. We can imagine them as a swarm of moon-sized to Mars-sized bodies circling the sun, each on its own path. They tugged at each other in passing, sometimes gently reshaping orbits, sometimes sending a neighbor careening into a new trajectory. Eventually, some paths crossed catastrophically. Two growing planet embryos might collide at tens of thousands of kilometers per hour, a titanic crash that could melt rock and strip atmospheres in an instant. These were the cosmic birthing pains. Out of violence came larger, more stable worlds. Each collision meant fewer bodies, but bigger ones. Gradually, the inner solar system's population winnowed down to 4 dominant survivors, the terrestrial planets, each bearing the scars of that tumultuous time in their craters and metal-rich cores. Meanwhile, further out, gravity was weaving even grander tapestries. In the cooler, more voluminous outer disk, a handful of colossal seeds were gathering mass at a relentless pace. Cores perhaps 10 times heavier than Earth aggregated, and once these cores were hefty enough, their gravity began to draw in the surrounding hydrogen and helium gas that permeated the disk. These future giants quickly bloated into immense spheres of gas around solid centers. Jupiter, the firstborn of the giants, might have been an early mover, a gluttonous core that vacuumed up gas and grew to monstrous scale. Not far behind, Saturn swelled into a second lord of the outer system. Uranus and Neptune were later to the feast, capturing what gas remained in their more distant orbits, and thus turning out smaller, but still becoming kings of the far cold region. Yet the giants did not form in peace either. They too felt the push and pull of gravity's caprice. Jupiter especially may not have been content to stay in its lane. Some scientists imagine a time when Jupiter wandered inward toward the Sun after it formed, like a restless titan lumbering through a crowded room, gravitationally scattering the smaller bodies in its path. In this scenario, Saturn's growth eventually pulled Jupiter back, their mutual gravities interacting in a complex dance that caused Jupiter to tack and migrate outward again. In its travels, Jupiter reshaped the layout of the young solar system dramatically. It swept some regions clean of would-be planets, robbed material from the inner disk, stunting the growth of Mars, which would end up much smaller than Earth, and hurled countless leftover planetesimals either into the Sun, out toward the distant Oort cloud, or inward to pummel the forming inner planets with a rain of impacts. Throughout this chaotic youth, impacts were unimaginably frequent. We call one period in particular the Late Heavy Bombardment, a time when the last leftovers of planet formation barraged the newly formed worlds. Every crater on Mercury, the Moon, and Mars is a memory of that era of incessant collision. Earth, too, was struck repeatedly, though wind and water have since erased most of those primordial scars. In those violent early days, a wandering rock the size of a mountain could obliterate a budding ocean or strip away a nascent atmosphere. And yet, paradoxically, some of these impacts may have also delivered vital ingredients, like water and carbon-rich compounds, to the inner planets, seeding the potential for future life. In the midst of this drama, our fledgling solar system gradually settled into a more ordered state. What had begun as a thick soup of dust and gas became a relatively flat disk with discrete, clear lanes, each dominated by a planet. The Sun's once raging winds calmed, blowing away much of the remaining nebular gas into interstellar space. The major planets had largely finished growing. Now they moved in defined paths, locked in by the Sun's gravity and each other's subtle tugs. The era of formation was giving way to an era of stability. The solar system was now a family of a star and its planets, orbiting in a majestic balance. Even so, some remnants of creation persisted, many minor bodies that never coalesced into planets. Between Mars and Jupiter, a band of rubble remained. The asteroid belt, composed of pieces of rock and metal that Jupiter's gravity had prevented from assembling into a world. And farther out, beyond Neptune, innumerable icy fragments lingered in the dark, forming a distant halo and belt of frozen relics. These leftovers would be the source of comets and meteorites for eons to come, cosmic messengers carrying clues of our origin. Thus, from the initial collapse of a dark cloud to a bright new star surrounded by planets, the solar system emerged. It is a story of violence and grace, destruction and creation hand in hand. Each world that survived carries the memory of those times, in craters, in tilted axes, in moons that likely formed from shattering impacts. The stage was now set. The Sun burned steadily at the center, and around it revolved a diverse cast of planets, great and small, each unique, yet bound by a common origin, each awaiting its own story in the unfolding cosmic drama. The Sun. At the center of it all blazes the Sun, a gentle tyrant, a brilliant guardian, the life-giver and occasionally life-taker. The Sun is our star, a true stellar furnace that has burned for billions of years and will burn billions more. In its core, the primordial fire kindled during its birth continues to rage quietly and ceaselessly. There, at temperatures of millions of degrees and under crushing pressure, hydrogen atoms fuse into helium, releasing energy that slowly percolates outward. What began as the faintest glimmer in the dark has become a roaring engine of nuclear fusion. The Sun's core is like a heartbeat for the entire solar system. Its steady output of energy is the pulse that warms the planets and defines the rhythms of day and night, season and year. From its bright face, the photosphere, streams the light that illuminates all our days. Photons born in the sun's core may take tens of thousands of years to fight their way out from the dense interior, bouncing from particle to particle in a chaotic journey, only to burst free at last and zip across space in 8 minutes to reach Earth. This sunlight is the visible sign of the sun's constancy. Every sunrise testifies that the sun is still there, still pouring out the energy that keeps Earth's oceans liquid and its forests green. To us, the sun appears eternal, unchanging, but it too lives a life cycle on a scale far beyond human lifetimes. For now, it is a stable middle-aged star, a yellow dwarf quietly converting 600 million tons of hydrogen into helium each second in its core. Though often symbolized as a serene golden disk, the sun is anything but tranquil. Its surface seethes and churns like a living thing. In giant loops and whirls of incandescent plasma, the sun's magnetic field rises through its surface, creating dark sunspots, island-like blemishes cooler than their surroundings, and enormous prominences that arc high above the stellar surface. From time to time, pent-up magnetic energy snaps in a sudden reconfiguration, unleashing solar flares and coronal mass ejections, colossal eruptions that hurl electrified gas into space at incredible speeds. These solar storms are the sun's more violent moods, and when they wash over the planets, they can spark ghostly auroras in polar skies and sometimes disrupt earthly technologies. The sun's benevolence comes with this volatile undercurrent, a reminder that our star, though nurturing, is a powerful and dynamic creature. Despite its tempestuous nature, the sun's influence is fundamentally stabilizing for the solar system. Its gravity holds all the planets in their orbits, like a parent keeping a firm grip on its children's hands. Each planet's path is a delicate balance between the forward urge of motion and the inward pull of the sun, a balance that results in graceful ellipses carved through space-time. The sun's gravitational embrace extends far, binding comets that wander hundreds of billions of kilometers away. Even there, the sun's faint tug still whispers guidance. It is the central anchor, the orchestrator of the celestial dance. To the ancient peoples of Earth, the sun was often regarded as a deity, a brilliant god whose daily rising and setting marked the very definition of time. And indeed, the sun is the ultimate arbiter of time in the solar system. A day is meaningful only in the context of a star's light and shadow. A year is quite literally one orbit around our sun. In this way, the sun's existence gives structure to the lives of all planets and any life forms upon them. When Earth spins on its axis, it is the sun's face that greets each turning, painting morning skies pink and evening skies amber. When distant Neptune crawls through a Neptunian year, 165 Earth years long, it is tracing an enormous circle around the sun, measuring out epochs in the slow cadence of that orbit. The sun's light is the metronome by which the solar system's symphony is played. Yet for all its mass, it contains 99.8% of all the mass in the solar system, and might, our sun is but a middling star in cosmic terms, one of hundreds of billions in our galaxy. It is not the largest or brightest possible, not the hottest or the coolest. But to us, it is uniquely precious. It has just the right properties to have allowed a planet like Earth to form and life to flourish. Its steady output has bathed Earth in stable warmth for eons, and its location in a less crowded part of the galaxy has spared us from frequent lethal supernovae nearby. The sun might even be considered a somewhat calm star, its variability modest enough that Earth's climate could remain relatively stable over geological time. For more than 4.5 billion years now, the sun has shone, gradually brightening as it slowly consumes its hydrogen fuel. It will continue to shine for several billion more. To the solar system, this means there is a long era of light within which all other dramas unfold. The planets can orbit secure in the light of a star that rises each day with unfailing radiance. And though the sun will not shine forever, in the scope of human existence, it is effectively eternal. We are cherished by a star in its prime. Look at the sun, carefully, indirectly, and you see a golden disk. But consider it more deeply, and you realize it is a cosmic furnace bound by self-gravity, a sphere of searing plasma held in delicate equilibrium. The inward pull of gravity tries to make the sun collapse, but the outward pressure of photons generated by fusion holds it up. In that balance, our sun finds its long-lived stability. It is often said that we are all made of stardust. Indeed, the sun's shine reminds us that stars transmute simple elements into more complex ones. The calcium in our bones, the oxygen we breathe, those were forged in earlier stars and cast into space, later to be incorporated into this solar system. In a way, the sun is both parent and sibling to us. Parent because it enables and sustains life, and sibling because it is born from the same ancestral cloud as all the rest of the solar system's matter, including the matter that makes up our bodies. In the solar system's family portrait, the sun is the radiant heart, occupying the throne at the center. Ever present, ever watchful, it binds the worlds together in its light. And as we now journey outward from the sun into the realm of the planets, we carry with us the understanding that each world is a fragment of that original cloud that also made the sun. They are its children and companions, forever linked to the sun's fate, warmed by its glow and guided by its gravity through the cosmic night. Mercury. Closest to the sun, a small scorched world races through space. Mercury, the innermost planet, is a tiny, airless and broiling sphere of rock and metal. It is the swiftest planet, completing a lap around the sun in just 88 Earth days, darting through the dawn and twilight skies of Earth like a fleet-footed messenger. In Roman myth, Mercury was the wing-footed messenger of the gods, and the planet fits its namesake well. It moves faster than any other planet, whipped around the sun by the star's intense gravity. Imagine standing on Mercury's surface. The sun looms more than 3 times larger in the sky than it does from Earth, and the daylight is a harsh white blaze pouring down relentlessly. There is no substantial atmosphere to scatter the sunlight or soften the heat. The sky is black even at noon, and the stars can be seen next to the glaring sun. On the rocky ground below, the landscape strongly resembles Earth's moon, pockmarked with innumerable impact craters from eons of collisions. This is a world that bears its history openly on its face. Every crater is a testament to a meteor strike, each scarp and cliff a result of the planet's crust shrinking and buckling as the interior cooled long ago. During Mercury's long day, 1 Mercury solar day lasts 2 Mercury years. The sun beats down on the ground without mercy. The day side heats up to incredible temperatures, hot enough to melt lead, baking the rocks and leaving them radiating infrared shimmer. Mercury has literally been sunburnt by its proximity to our star. But when night falls, which on Mercury happens only after the planet has rotated very slowly, Mercury rotates on its axis only 3 times in 2 of its years. The heat escapes swiftly into space. With no air to trap the warmth, the temperature plunges precipitously. The night side of Mercury is colder than the depths of a freezer, capable of freezing gases solid. In this way, Mercury experiences the most extreme temperature swings in the solar system, from fiery day to bitter night, a testament to the absence of any atmospheric blanket. Crater after crater covers Mercury's terrain, from tiny pits to giant multi-ringed basins hundreds of kilometers across, evidence of a violent youth. One enormous impact basin, Caloris, hints at the colossal strike Mercury endured. On the opposite side of the planet, the terrain is jumbled and chaotic, likely jostled by the focusing of shockwaves through the planet during that ancient impact. Mercury's surface, grayish-brown and dusty, glints in the stark sunlight, and bright streaks of ejected material, called crater rays, sprawl out from some newer craters, decorating the old surface with younger scars. Despite being so close to the Sun, Mercury harbors a few surprising secrets. At its poles, hidden in the permanent shadows of deep craters where sunlight never reaches, there are deposits of water ice. Comets, or perhaps water-bearing meteorites, likely delivered this ice, and in these shadowed pockets, cold traps, the ice has persisted over millennia, a curious frost in an oven-like world. Mercury also has a global magnetic field, a miniature version of Earth's magnetic bubble, suggesting that inside Mercury's small frame, the iron core is still partly molten and moving, generating magnetism. This core, disproportionately large relative to the planet's size, Mercury is about 70% metal by mass, hints that Mercury might be the remnant of a larger world that lost some of its outer rocky layers early on, perhaps stripped away by a giant impact or by the young sun's fierce heat. If one could listen to Mercury, though airless worlds carry no sound, one might imagine a deep silence interrupted only by distant thuds of micrometeorites. The planet seems frozen in deep time, its geology long ceased except for occasional tremors from impacts. There are no flowing rivers or shifting tectonic plates to renew the surface. What happened billions of years ago is still visible today. In Mercury's ancient, cratered face, we see a fossil record of the solar system's infancy, preserved by a lack of erosive forces. From afar, Mercury often appears as a bright star-like point near the Sun, elusive in the Sun's glare. It never strays far from the Sun in Earth's sky, always immersed in twilight. This perpetual proximity defines Mercury's character. It is the innermost companion of the Sun, locked in a 3-2 spin orbit resonance, meaning it rotates 3 times on its axis for every 2 orbits around the Sun. This resonance causes Mercury's day to be extraordinarily long relative to its year. Dawn to dusk on Mercury lasts about 3 Earth months, a long, slow roasting followed by an equally long, deep freeze. Mercury may be small, only slightly larger than our Moon, but as the first planet from the Sun, it stands as a testament to extremes. It is a world of light and darkness, searing heat and frigid cold, a little battered sphere that rushes around the Sun with cosmic urgency. It illustrates how diverse the children of the Sun can be, even those born of similar stock. As we leave Mercury and venture further out, we will see how each additional step from the Sun brings new environments, new extremes, and new tales, all under the governance of our central star, Venus. Veiled in brilliance, Venus is the second planet from the Sun, and in many ways, the most enigmatic. To the eye, Venus is a gentle, ivory beacon, the brightest object in Earth's night sky after the Moon, often seen shining like a heavenly jewel in the twilight. This radiant appearance earned Venus the title of goddess of love and beauty in myth, a celestial Aphrodite. Yet beneath that lovely veil of clouds lies a world dramatically inhospitable, a planet of oppressive heat, crushing pressure, and an atmosphere laced with acid. Venus is a study in contrasts, twin to Earth in size and composition, but a hellish twin, cloaked in mystery and harshness. Imagine descending through Venus's cloud layers. The upper atmosphere is a high canopy of yellow-white clouds composed of tiny droplets of sulfuric acid. Winds there are ferocious, circling the planet in mere days, a phenomenon called superrotation. As you sink through this toxic haze, the sunlight dims to an orange glow, filtering through perpetual cloud cover. Deeper down, the air grows hotter and thicker with every kilometer. By the time you approach the surface, you're in a murky orange-brown light, like a perpetual overcast dusk. The temperature has soared to a level hot enough to melt lead, and the pressure is a crushing 90 times heavier than Earth's, as if you were nearly a kilometer beneath the ocean. On the ground, if you could stand there, you would find yourself amid a barren landscape of rocks and gently rolling plains. with some highland rises in the distance. The heat is so intense that the rocks themselves faintly glow dull red. The atmosphere around you is a dense soup of carbon dioxide, laced with nitrogen and trace chemicals, and so thick that it feels almost like a fluid. There is no water. Any oceans Venus may have once had are long boiled away. The ground shows evidence of volcanic fury, enormous shield volcanoes broad and tall, vast fields of solidified lava, and strange features called coronae, where the crust has been deformed by upwelling magma. Venus is remarkably flat in many regions, but dotted with these volcanic highlands and ridges, suggesting that volcanism has been a dominant force. The air, so hostile to us, creates an unimaginably strong greenhouse effect. Sunlight penetrates the clouds and warms the surface, and the surface in turn radiates heat. But the thick carbon dioxide atmosphere traps this heat efficiently, allowing almost none to escape. The result is a runaway greenhouse, a world where the heat just builds and builds until it can balance out only at extraordinary temperatures. This process has made Venus's climate the most blistering in the solar system, a stark warning of the power of atmospheric chemistry. And yet, ironically, high above that inferno, in the cooler cloud tops, conditions are more clement, around Earth-like temperatures and pressures. Some have wondered if simple life could exist up there in the temperate cloud decks, riding the winds in droplets of acid far above the dead ground. It is a fanciful thought, with no evidence yet, but it shows how even in Venus's extremity, we search for possible footholds of life. So far, Venus reveals only a harsh lesson. Two planets so similar in birth can end up with vastly different destinies. Where Earth became a water blue haven, Venus became a toxic pressure cooker. Something tipped the scales. Perhaps it was Venus's slightly closer position to the Sun, a touch more sunlight that sent it down a path of evaporating oceans and a sky thickening with carbon dioxide, each reinforcing the other in a vicious cycle until the oceans were gone and the rocks themselves released gas under the heat, filling the atmosphere with a choking density. Venus, in this sense, is a tale of what might have been for Earth, a vision of a habitable world lost to extreme greenhouse fury. For billions of years, Venus has sat under its shroud of clouds, rotating slowly backwards. It spins in the opposite direction to its orbit, unlike most planets. A day-night cycle on Venus is thus complex. One Venusian day, sunrise to sunrise, lasts longer than its year. But on the ground, time would lose meaning in the unchanging murky light. No stars are visible, no blue sky, only a dim orange glow by day and pitch darkness by night. If you had a flashlight, you might see a metallic sheen on some rocks. In the highlands, strange snows of lead sulfide and bismuth sulfide frost the surface, condensing out of the atmosphere in cooler elevations. It snows metal on Venus's peaks, a bitter parody of the gentle snows on Earth. Despite its inhospitable nature, Venus holds a certain fascination. From Earth, we always see its clouds, never its surface directly, until the advent of radar mapping, which unveiled its tortured terrain beneath. For ancient sky watchers, Venus was a mystery, a beautiful star that never strayed far from the sun, appearing either at dawn or dusk. They called it the morning star and evening star, unaware it was the same object. Venus has inspired myths of love and beauty, ironically so given its true nature. In a poetic sense, Venus teaches that appearance can mask reality. A gorgeous jewel can hide a cauldron. We leave Venus with a mix of awe and relief. Awe at its dramatic character, relief that our own world is not so unforgiving. Looking back, we see Venus as a smooth white disk, its secrets hidden. It drifts on its orbit, veiled and impenetrable, a warning glimmer in the sunrise sky. And beyond Venus lies the one oasis we know in all the darkness, the blue marble of Earth, our home, beckoning with its color and life. Earth. Behold Earth, the third planet from the Sun, our home, the living world, the ocean planet, the cradle of life as we know it. From the vantage of space, Earth is a marvel of blue and white, vast sapphire oceans swirled with patterns of white clouds, set against the deep, ruddy brown and emerald of continents. It is at once delicate and dynamic. In Earth, the solar system reveals a masterpiece of balance, a realm where air, water, rock, and life intertwine to create something unique. Imagine approaching Earth from afar. Long before you see the details of continents or islands, you notice the hue, a distinctive blue halo around the planet. That is the envelope of air and ocean, water in liquid, solid, and vapor forms that makes Earth unique. As you come closer, you see the polar ice caps gleaming white, the banded whirls of weather systems curling over landscapes, the glitter of sunlight off broad seas. Here is a planet at the perfect distance from the sun for liquid water to persist on its surface, not boil away, not remain perpetually frozen. Earth sits in what's often termed the Goldilocks zone, the just right conditions that have allowed rivers to flow, rains to fall, and life to emerge and evolve. On the surface, Earth is a wonderland of complexity. High mountains pierce the sky, deep ocean trenches plummet into darkness, rolling plains and high plateaus, vast deserts and dense forests, tundra and tropics. Earth's geography is varied almost beyond imagination, sculpted by tectonics and erosion and the ceaseless cycles of water and wind. Unlike its barren siblings, Earth's surface is continually renewed and reshaped. Volcanoes belch fresh rock from interior furnaces. Earthquakes jolt entire regions as giant crustal plates shift and grind, evidence that Earth's interior remains geologically alive. This plate tectonics not only builds mountains and pulls continents apart, but also plays a role in regulating the planet's climate over eons, in concert with the oceans and life itself. Life on Earth runs riot in countless forms, from simple, single-celled bacteria hiding in scalding vents to the complexity of whales and redwood trees and human beings. It infiltrates every niche. Life swims in the highest atmosphere, creeps in the driest deserts, thrives in boiling hot springs and the crushing black depths of the sea. Over 3.5 billion years, life has interacted with Earth in a profound symbiosis. Plants and algae breathed in carbon dioxide and exhaled oxygen, gradually transforming the atmosphere into an oxygen-rich mix that allowed animals to flourish. Microbes in the soil helped break down rocks, and the very presence of life accelerated the formation of soils and the cycling of elements. Earth's current atmosphere, 78% nitrogen, 21% oxygen, with traces of argon, carbon dioxide, and others, is in fact a byproduct of living processes and geologic outgassing. It's a dynamically maintained mixture that shields the surface from harmful radiation thanks to an ozone layer high above, and keeps the planet warm enough for water to remain liquid thanks to mild greenhouse gases like carbon dioxide and water vapor. From the ground looking up, Earth's sky is a serene blue by day due to air molecules scattering the sunlight. Cottony clouds form and dissipate, carrying water from ocean to land as rain and snow in an endless hydrological cycle that nourishes ecosystems and sculpts the land via rivers and glaciers. At night, the same sky reveals the cosmos beyond, but also often glows with the lights of human cities. For humans, one form of life, have learned to harness fire and electricity, altering the nocturnal face of the planet. In polar nights, one might witness auroras, shimmering curtains of green and red light, as Earth's magnetic field channels solar wind particles into the upper atmosphere, a gentle reminder of the sun's reach and Earth's protective magnetosphere. Earth's magnetic field, generated by a spinning molten iron core, forms a protective cocoon around the planet, the magnetosphere, that deflects many of the charged particles from the Sun. Without it, our atmosphere might have been gradually stripped away by solar wind, as likely happened on Mars. This magnetic shield, along with Earth's gravity and active geology, helped Earth retain its oceans and air, which in turn enabled life to take hold and flourish. And life has in turn affected geology. For example, limestone and other sedimentary rocks are largely composed of shells and skeletons of once living things, sequestering carbon and shaping Earth's long-term climate. No other planet we know of has the combination of features Earth does. In the solar system's symphony, Earth's role is that of the fertile oasis, the one place where the chemistry of life took root in a significant way. Mars may have had brief episodes of habitability, and perhaps some icy moons harbor life in their hidden seas. But Earth shouts life from its every pore. One might consider Earth and Venus as a cautionary dichotomy, similar in bulk, but divergent in outcome. Why one became Eden and the other a furnace is a question that underscores how finely poised planetary evolution can be. Earth's distance from the Sun, its initial endowment of water, its moderate size allowing it to hold onto its atmosphere, but not so large as to become a gas giant, its vigorous plate tectonics recycling carbon. All these factors combine to create a stable, life-friendly environment over geologic timescales. Remove or alter one piece, and the story could have been very different. From the vantage of an outside observer, Earth's atmosphere betrays its living nature. The large amount of oxygen is a dead giveaway. Oxygen is highly reactive and without continuous replenishment by life, through photosynthesis, it would quickly bind with rocks and vanish from the air. The presence of methane, also out of equilibrium, hints at organic activity. Methane is produced by microbes and other processes. A spectroscopic glance at Earth from afar would suggest something unusual is afoot. That is the very method we now dream of using to find living worlds around other stars. Earth, in that sense, is our proof that planets can be alive. To us, though, Earth is home. It is the world that cradled us from our evolutionary infancy. All our myths, our histories, our triumphs and tragedies, everything has happened on this pale blue dot, as astronomer Carl Sagan so famously dubbed it, when Voyager 1 took a farewell photo of Earth from beyond Neptune. From that distance, Earth was a tiny speck suspended in a sunbeam, emphasizing our smallness. Yet contained in that speck is everything we hold dear, every experience, every living creature known. Earth is, so far, the solar system's crowning jewel, not because of gems or precious metals, but because it hosts the rarest treasure, life and consciousness. As we journey onward to other worlds, we carry with us the mental image of Earth, a reference point and a comfort. The gentle blues and greens of Earth remind us that among the cold and airless or seething and toxic landscapes of other planets, there exists a sanctuary. Earth's existence encourages hope that such sanctuaries might exist elsewhere too. It also serves as a reminder of our responsibility. As the only known, life-bearing planet, Earth's health is precious and within our power to influence. Just as Venus warns of greenhouse fury, Earth demonstrates climate balance, but also how vulnerable that balance can be to perturbation. In our exploration of the solar system, we have gained perspective on Earth's fragility and resilience. Leaving Earth in our tour, we find ourselves at once proud and wistful. Proud that our planet thrives, that it has told a remarkable story of stability amid change for billions of years. Wistful, because as we step away into the rest of the solar system, Earth's warmth and breathable air are left behind, unique in a cosmos that, as far as we've seen, offers no second Earth nearby. The journey must continue outward, but the heart of any traveler may always remain tethered to Earth, beating in rhythm with the familiar cycle of day and night and the gentle seasons bestowed by the sun. Mars. Mars, the fourth planet from the Sun, has long captured human imagination more than any other. The quintessential red planet, Mars glows in our night sky with a steady, rusty hue like an ember of a distant fire. Smaller than Earth, quieter than Earth, Mars today is a cold desert, a place of pink skies and salmon-colored soil, of towering volcanoes long extinguished and canyons that dwarf any on Earth yet run dry as bone. It is a world seemingly at rest, its air thin, its waters mostly locked in ice. Yet everywhere on Mars, there are echoes of a more dynamic past. It beckons to us with the tantalizing question, could it have once harbored life? And might it yet in hidden niches? Approach Mars, and the first thing that strikes you is its color. Iron oxide, rust, permeates its dust, giving the planet a uniform ruddy complexion. Swirling dust storms can engulf the whole globe in a pale orange haze, and at other times you can see dark basaltic rock patches and bright rusty plains with white caps at the poles where carbon dioxide and water ices reside. The sky on Mars, unlike the deep blue of Earth, is often a butterscotch or salmon pink, colored by fine dust suspended in the tenuous air. Stand on Mars's surface during the day, and the sun, farther and fainter than we know, bathes the landscape in a warm, coppery light. By night, the sky is black and sharp, with Phobos and Deimos, Mars's two tiny potato-shaped moons, racing across the heavens. The Martian terrain is a study in extremes. In the north, broad smooth plains stretch out, likely the beds of ancient oceans or vast lava flows. In the south, highlands rise, heavily cratered with the scars of ancient impacts, telling of great age. Cutting along the equator is the titanic gash of Valles Marineris, a canyon system that would span the width of North America, with cliffs towering many kilometers high. It looks as if Mars has been slashed by some giant claw, but in truth, it likely formed from the planet's crust cracking as it swelled in places due to tectonic forces or the upwelling of magma. On the Tharsis Rise nearby stand the largest volcanoes in the solar system, including Olympus Mons, a volcano roughly 22-kilometer high, nearly triple Mount Everest's height, and so wide at its base that you could stand on its slopes and not realize you were on a mountain. These shield volcanoes built up over eons of eruptions, but their lack of young lava flows indicates they have been dormant for perhaps millions of years. Mars's inner heat waned long ago. Its great volcanoes have gone cold, and its global magnetic field faded, leaving only patchy remnants in ancient rock. But perhaps the most profound tales of Mars lie in subtler features: dry riverbeds, delta fans, minerals that form in water, and rounded pebbles that once tumbled in streams. Mars today is a desert, but in its youth it was more Earth-like. We see evidence that long ago, liquid water flowed freely on its surface. Sinuous valley networks etched into southern highlands suggest rain once fell and collected into rivers. Enormous outflow channels in other regions imply cataclysmic floods may have rushed across the surface, carving teardrop-shaped islands around obstacles and pooling into temporary lakes or a northern ocean. Layered sediments, spotted by rovers and orbiters, hint at ancient lakebeds that persisted for thousands of years in craters and lowlands. The rover Curiosity found slabs of rock in Gale Crater that bear the signature of gentle river deposits, conglomerates of rounded stones in an ancient streambed, and drilled samples revealing clays, minerals that require water and moderate pH to form. All these lines of evidence converge on a picture. Billions of years ago, Mars was warmer and wetter, at least episodically. Its atmosphere, now thin and unable to support liquid water at the surface, must have been thicker then to allow a stable water cycle. Perhaps early Mars had a dense blanket of carbon dioxide and maybe other greenhouse gases, enough to trap solar heat when the sun was dimmer than today. For a time, Mars could have had cloudy skies, rainfall, lakes, and shallow seas, and rivers snaking across its surface. If life ever began on Mars, that would have been its window of opportunity. It's conceivable that microbial life could have gained a foothold in Martian lakes or hot springs. Today, with Mars as cold as it is, average surface temperature about 60 degrees, though it can reach 20 degrees Celsius at noon at the equator in summer and drop to 125 degrees Celsius at night. And with surface water locked up in permafrost or polar ice, any life would have had to retreat to refuges like the subsurface, where geothermal warmth or salt brines might still sustain liquid water pockets. Mars tantalizes us with possible hints. For example, methane has been detected in its atmosphere in fluctuating amounts. On Earth, much methane is biological in origin, though geologic processes can also produce it. On Mars, the spikes of methane could be coming from subsurface bacteria releasing gas during warmer seasons, or from chemical reactions between water and certain rocks. We simply don't know yet, but the possibility keeps our eyes on the red planet as a prime target in the search for extraterrestrial life. The Martian air is thin, about 1% the surface pressure of Earth's, and composed mostly of carbon dioxide. It's too thin to effectively transfer heat, which is why nights get so cold. It's also thin enough that liquid water is not stable. It either freezes or boils away. Often it sublimates directly from ice to vapor. However, Mars does have weather. Thin as it is, the atmosphere can muster winds that create dust devils whirling across the plains, and seasonal CO2 frost that forms in winter near the poles and sublimates in spring drives wind patterns, even creating geysers of gas that disturb dust on the polar ice. Every few years, Mars experiences global dust storms that enshroud the entire planet in haze for weeks or months, as observed from Earth and by our orbiters. These storms can dim the surface so much that solar-powered robots like the Opportunity rover went into hibernation. Indeed, one such storm in 2018 was so severe that Opportunity did not recover, reminding us that Mars, though seemingly inert, still has the power to surprise and overwhelm. Mars's two moons, Phobos and Deimos, are tiny, likely captured asteroids, and orbit very close. Phobos, the larger one, is so near Mars that it actually orbits faster than Mars rotates, meaning it rises in the west and sets in the east, crossing the sky in about 4 hours. It is destined in tens of millions of years to either crash into Mars or be torn apart into a ring as it spirals inward. For now, these moons are little more than lumpy placeholders in the Martian sky, but to future explorers, they may serve as stepping stones or station locations. One cannot mention Mars without acknowledging the human aspect. Of all planets, Mars is the one we have most dreamed of visiting, and indeed the one we have explored most with robotic emissaries. The names Spirit, Opportunity, Curiosity, Perseverance. These are rovers that have traversed Martian ground, acting as our eyes and hands. They have found ancient stream beds, tasted minerals formed in water, and snapped awe-inspiring panoramas of alien deserts and sunsets with a blue tinge. Mars's dust causes the sun at day's end to appear bluish. The Mars orbiters have mapped dried-up lakes and even detected subsurface ice deposits nearly everywhere, sometimes just a meter below the dusty crust. We've even heard the whisper of Martian wind, recorded by a rover's microphone, a soft, eerie breeze from a world that once might have carried the laughter of brooks and waterfalls. Mars grabs at our imagination because it is a mirror of sorts. A smaller Earth that didn't quite thrive, a world that started with such promise and then fell dormant. Standing at dusk on Mars, one might feel a poignant desolation. The horizon is sharp and close due to the smaller globe. Gravity is only 38% of Earth's, so your steps feel lighter, your jumps carry you higher. The silence is profound, broken only by the crunch of your boots on the iron-rich sand, or perhaps the distant whisper of a dust devil. Overhead, if it is near twilight, you might see Earth as a bright star appearing in the evening sky, a wandering star for Mars, much as Venus is for Earth. How poetic that would be, to stand on Mars, the long-dreamed-of planet, and gaze back at Earth, our shining blue home, hanging in the Martian sky. Mars is often called the Red Planet, but perhaps the Remembering Planet would be apt. It remembers a time of running water and perhaps life. It holds those memories in dried river channels and the chemistry of its stones. To unlock those secrets, we continue to send missions and plan for human footprints on Martian soil. Mars, silent now, might one day ring with human voices as new chapters in the saga of life in the solar system are written. For now, we leave Mars with its questions mostly intact and journey onward, further from the sun's warmth, into realms where sunlight is but a feeble glow and worlds are made not of rock alone, but of gas and ice and spectral rings. The Moon. Orbiting Earth is a faithful companion, our moon, a silvery pearl in the night, the first stepping stone into the cosmos for humanity, and a sentinel that has witnessed Earth's history from the very beginning. The moon is more than just Earth's satellite. It is a part of Earth's story, born of cataclysm, and now a driver of gentle rhythms like tides and eclipses. Throughout human existence, the moon has been a source of wonder, inspiration, and guidance. Yet its origin is violent. The moon likely formed from the debris of a titanic collision in the early solar system, an event that forever changed Earth's destiny and gave us the beautiful orb we see glowing in our sky. Travel back about 4.5 billion years, when Earth was newly formed and still recovering from the chaos of accretion. A wandering protoplanet, roughly the size of Mars, is believed to have struck Earth a glancing blow. This cataclysmic impact tore out a huge portion of Earth's mantle and sent it into orbit as a spray of molten rock and vapor. Within weeks or months, gravity gathered that debris into a sphere, the infant moon, glowing red-hot in Earth's sky, much closer than it is now. Over time, the moon cooled and solidified. Evidence of this origin story is found in the lunar rocks. They share chemical fingerprints with Earth's crust, yet show signs of formation in an environment depleted of lighter elements, consistent with being born from a superheated disk around Earth. Thus, the moon is literally made of Earth, a child of Earth born from violence. As the ages passed, the moon drifted away from Earth, gradually moving to the roughly 384,000 kilometer distance it resides at today, and it continues to recede by a few centimeters per year, a subtle farewell in progress. The moon's appearance evolved. Early on, it was covered by a magma ocean which crystallized into a lighter crust. The relentless bombardment of leftover comets and asteroids pounded its surface, creating countless craters and basins. Some impacts were so large they cracked the crust. Later, molten rock from the moon's interior welled up to fill those giant basins, smoothing them into the dark maria or seas, which are not water seas, but great plains of solidified lava. These lunar maria, mostly on the side facing Earth, form the familiar man-in-the-moon patterns that humans have gazed at for millennia. The maria are relatively younger, though still over 3 billion years old, and less cratered, whereas the bright highlands represent the moon's older crust, saturated with impact scars. Since that early flurry of volcanic activity waned, the moon has been geologically quiet. No air, no flowing water, no plate tectonics to renew its surface. It is a museum of ancient history, its craters preserving a record of the heavy bombardment that all inner worlds suffered. Standing on the moon is an experience only a few humans have had so far. The sky above is deep black even when the sun stands high, because there is no atmosphere to scatter light. The sunlight is fierce and unfiltered. Shadows are stark and pitch dark. The ground is grey dust and rock, fine like powder in many places. A regolith created by billions of years of meteorite impacts, grinding the rocks to dust. Horizons on the moon are closer and smaller due to the moon's petite size. You can almost sense the curvature standing on a mere plane. Gravity is 1/6 of Earth's. One could bound in great loping strides and lift heavy rocks with ease. In the daytime, the surface underfoot can heat to 120 degrees, while at night it plunges to 170 degrees, extremes moderated only slightly by the slow lunar day-night cycle. The moon turns once relative to the sun every 29.5 Earth days. The most striking sight, of course, from the moon's surface is Earth itself. A blue marble hanging in the black sky, 4 times bigger in apparent diameter than the moon is from Earth's perspective, and almost unmoving. The Earth hovers nearly in the same spot because the moon's rotation is locked to its orbit, always showing Earth the same face. To early lunar visitors, Earth looked like a fragile oasis suspended in emptiness, a profound sight that underscored our place in the cosmos. The moon's presence has been crucial for Earth in subtle ways. It stabilizes Earth's axial tilt, thanks to its gravitational pull, preventing wild swings in orientation that could cause chaotic climate shifts. Instead, Earth's tilt oscillates only slightly over long periods, giving us relatively stable seasons. The moon also raises tides in Earth's oceans, a rhythmic ebb and flow that may have been important for early life transitioning from sea to land, and which even now shapes coastal ecosystems and circulates nutrients. By tugging on Earth's waters, and to a lesser extent the crust, the moon has acted like a mixing spoon for our planet's environment. Additionally, over geologic time, tidal friction from the moon's pull has gradually slowed Earth's rotation. In the age of dinosaurs, a day was perhaps 22 hours, now it's 24. That same interaction has propelled the moon gradually farther away. The Earth and moon share a tidal relationship. The moon is fully locked to Earth, hence the same side always faces us, and Earth's day is slowly lengthening in response. In cultural and emotional terms, the moon has been a beacon for humanity's imagination, a symbol of romance, a keeper of time, many calendars were lunar, and an object of aspiration. When Neil Armstrong set foot on the moon in 1969 and uttered, "One small step for a man, one giant leap for mankind," it marked a turning point in how we view the moon, not just as a distant orb, but as a reachable world. Footprints still lie undisturbed in the lunar dust at the Sea of Tranquility and other Apollo landing sites, preserved perhaps for millions of years, unless meteoroid impacts scour them away. Those probes succumbed in mere minutes to the heat and pressure, but they confirmed Venus's harshness once and for all. From Earth, we observe Venus's thick clouds reflecting sunlight brilliantly. Hence Venus is our morning star or evening star, never straying far from dawn or dusk. Its bright, beautiful presence has inspired humans for millennia. How poignant that this beauty is a veil over a world of such extreme conditions. Venus reminds us that twins can grow apart, that a planet so similar to Earth in bulk can be so different in fate. It warns us of the fine line between habitability and disaster. But Venus is also a testament to the dynamism of planets. It has its own story of interior heat and volcanic fury, of atmospheric chemistry and climate run amok. In the grand balance of the solar system, Venus resides between the scorching austerity of Mercury and the vibrant life of Earth. It is a world of fire and poison clouds, a vision of a once potentially Earth-like world now lost to extreme greenhouse fury. If Earth is a haven, Venus is a warning. As we depart Venus's vicinity, one cannot help but feel gratitude for Earth's comparatively gentle environment. And yet, there's also admiration for Venus, the bright beacon of dawn that, despite its inhospitable face, remains one of the solar system's most fascinating and instructive characters. We look up on a clear night and see thousands of tiny lights sprinkled across the sky. From ancient times to the present, people have been captivated by the stars. They have inspired wonder, guided travelers, and sparked countless myths and legends. Humans imagined patterns in them and told stories about gods, heroes, and animals in the heavens. We use the stars to navigate oceans and to mark the seasons. But what are these brilliant pinpricks of light, really? Stars are giant, luminous balls of plasma, held together by their own gravity and powered by nuclear fusion at their cores. In simple terms, a star is a colossal nuclear furnace in space, constantly fusing lighter elements into heavier ones and releasing tremendous energy as light and heat. They seem eternal and unchanging to us, but in reality, stars are born, they age, and they die, undergoing dramatic changes over millions or billions of years. Our Sun is one such star. In fact, it's the only star close enough for us to feel its warmth and light directly. And it's just one among an uncountable multitude of stars in the universe, each with its own story. Now, imagine journeying into a vast cosmic cloud far out in space, where new stars are born. These regions are called nebulae, enormous, diffuse nurseries of gas and dust sprinkled throughout the galaxies. They are the cradles of star formation. If you could float inside one, you might see faint, ghostly glows and dark, opaque patches where starlight from outside is blocked. The famous pillars of creation. Photograph of the Eagle Nebula, for instance, shows towering columns of gas and dust rising like mountainous spires. Within those cold, shadowy pillars, new stars are slowly taking shape. The Great Orion Nebula, visible as a faint smudge in Orion's sword, is one such stellar nursery, a cavern of gas and dust over 20 light-years wide, where thousands of baby stars are forming. Here, in the cold, dark depths of a nebula, the story of a star begins. A slight nudge, perhaps the shockwave from a distant supernova or a random density fluctuation, causes parts of the cloud to begin collapsing under their own gravity. Over thousands to millions of years, a portion of the nebula's gas gathers more and more mass, pulling in surrounding material. As this pocket of gas shrinks, it grows denser and hotter, and it starts to spin faster. Eventually, it forms a growing ball of gas known as a protostar, a baby star that's still gathering mass. Surrounding it, a flat disk of gas and dust often forms, whirling around the protostar. Protostars also often fire out bipolar jets, narrow beams of gas blasting out from their north and south poles. These high-speed jets can plow through the surrounding nebula, creating glowing shockwaves and carving cavities in the cloud. The protostar at the center continues to contract and heat up as gravity relentlessly squeezes it. Deep in the core of this protostar, temperatures climb into the millions of degrees. The gas is mostly hydrogen, the simplest and lightest element. When the core temperature reaches roughly 15 million degrees Celsius, something miraculous happens: ignition. Hydrogen nuclei begin to fuse together to form helium, unleashing a tremendous amount of energy. This is the moment a star is truly born. The protostar has become a full-fledged star, blazing with its own light. The once dark core suddenly glows brilliantly, and the outward pressure of this new energy release halts the gas collapse. The infant star turns on, so to speak, and starts shining. The surrounding cocoon of leftover gas and dust gets blown away by the fierce stellar winds and radiation now pouring from the newborn star. The star stabilizes, no longer contracting, as a balance is struck. It has entered the long, stable phase of its life, known as the main sequence. Often, stars do not form alone. Many newborn stars come in groups called star clusters. Our Sun likely formed in a cluster with several sibling stars, which have since drifted away. Once nuclear fusion starts in the core, a star finds an equilibrium. Outward pressure from the fusion energy balances the inward pull of gravity, and the star stops shrinking. It becomes stable, neither collapsing nor exploding, steadily glowing. The star will remain in this state, fusing hydrogen in its core, for the vast majority of its lifetime. It's as if the stellar engine is idling at a steady rate. This newfound stability allows the star to shine consistently for a very long time. Millions, even billions of years will pass with the star in this tranquil main sequence phase. Our Sun is in fact in this phase right now and has been for about 4.6 billion years. This stability is fortunate for us. It means the Sun's energy has been steady enough to allow life to develop on Earth and will continue for eons more. If our Sun were a short-lived massive star, life as we know it might never have had the chance to arise in the brief stellar lifetime. Main, sequence stars like the Sun quietly convert hydrogen to helium, radiating energy into space and providing warmth and light to any orbiting planets. In this main sequence stage, a star shines by nuclear fusion, fusing hydrogen atoms into helium in its core, and in doing so, it releases an absolutely colossal amount of energy. To give a sense of scale, our Sun fuses about 600 million tons of hydrogen every second, turning it into about 596 million tons of helium. The missing mass, roughly 4 million tons per second, is converted to pure energy according to Einstein's famous equation E=mc². 4 million tons of matter turned into energy every single second. This energy then radiates outward from the core, through the Sun's layers, and eventually into space as heat and light. The numbers are mind-boggling. The Sun's energy output each second is about 3.8 × 10⁻²⁶ watts, a figure almost impossible to imagine. To put it in human terms, the power the Sun releases every second is equivalent to the energy from billions of nuclear bombs exploding at once. Yet this gargantuan output has been running continuously for billions of years, and will continue for billions more. It's sobering to realize that for most of human history, the source of the Sun's power was a mystery. Only in the 20th century did scientists like Arthur Eddington and Hans Bethe figure out that nuclear fusion is what makes the stars shine. Millions of such stars fill our galaxy, each a massive energy source blazing in space. Not all stars are like our Sun, however. Stars come in a stunning variety of sizes, colors, and luminosities. Some are far bigger and hotter than the Sun, shining blue, white, and piercingly bright. Others are smaller and cooler, glowing a faint red. The color of a star is a clue to its surface temperature. Hotter stars emit more blue, white light. Cooler stars more red, orange light. For example, in the constellation Orion, you can spot a contrast between the supergiant star Betelgeuse, which shines with a reddish hue, and Rigel, which gleams bluish-white. In general, a blue star might be tens of thousands of degrees at its surface, while a red star might be only a few thousand degrees. These differences correspond to spectral classes. Another example, the star Sirius, the brightest star in Earth's night sky, is about twice the Sun's mass and has a surface temperature of around 9,400 K, giving it a white-blue sparkle. On the other hand, our Sun is yellow, white, and a typical small red dwarf star would look deep red to our eyes. The vast majority of stars in our galaxy are actually small, cool red dwarfs. Perhaps 70–80% of all stars fall into this category. These red dwarfs are so dim that not a single one is visible without a telescope. In fact, the smallest true star ever measured is only slightly larger than the planet Saturn. With just about 8% of the Sun's mass, it barely manages to sustain fusion. Were it any smaller, it would fail to ignite and become a failed star, known as a brown dwarf. By contrast, most of the stars we see sparkling in the night sky are the larger, more luminous types that, while much rarer, shine hundreds or thousands of times brighter than red dwarfs and can be seen across great distances. If you stood on a hypothetical planet orbiting a red dwarf, the star might hang in a dim red sky, casting an eerie dusk, like light even at noon. By contrast, a planet around a hot blue-white star would be flooded with a stark, bluish illumination, and intense ultraviolet rays. Size and mass have a profound effect on a star's fate. In general, the more massive a star, the hotter and brighter it burns, and the shorter its life. A star 10 times more massive than the Sun might emit thousands of times more energy, blazing a brilliant blue, white, but it will use up its fuel at an unsustainable rate. It's the difference between a gas, guzzling sports car and an economy car. The massive star burns through its fuel quickly, while a small star is extremely fuel efficient. Massive stars live fast and die young in a cosmic sense. Such a star might last only a few million years before it exhausts its core fuel. In contrast, a tiny red dwarf sips its hydrogen fuel so slowly that it can continue burning for hundreds of billions or even trillions of years. To put it in perspective, the universe itself is about 13.8 billion years old, so no red dwarf has had time to even come close to dying yet. Our Sun lies somewhere in the middle of the mass range. It's a G-type yellow dwarf, not exceptionally massive or small. It will have a total lifetime of roughly 10 billion years, moderately long by stellar standards. So far, the Sun has been shining for about 4.6 billion years, and it has about 5 billion to go before it starts to run out of core hydrogen. Because of these lifespan differences, no red dwarf star has ever died in the history of the universe. The universe simply hasn't been around long enough for the smallest, slowest, burning stars to use up their fuel. Even the oldest red dwarfs, born shortly after the Big Bang, are still shining today and will keep on shining for trillions of years to come. By the far distant future, long after bigger stars like the Sun have died, red dwarfs will be the last stars remaining, quietly glowing red in a fading universe. On the other end of the spectrum, many massive stars have lived and died in that same time, blazing through their fuel in a few million years and ending in catastrophic explosions. In a sense, the cosmos has a way of favoring the slow and steady when it comes to longevity. Eventually, even the most long-lived star will run low on fuel. When a star has fused most of the hydrogen in its core into helium, it starts to leave the stable phase of its life. The delicate balance that maintained the star for so long begins to falter. With less nuclear energy being produced in the core, the outward pressure that held the star up drops. The core, now largely helium, begins to contract under gravity since nothing is pushing back as strongly. And when the core of the star contracts, surprising things happen in the layers around it. The contracting core heats up a lot. This intense heat radiates into the surrounding shell of hydrogen that wasn't previously hot enough to fuse. Now that shell of hydrogen does begin fusion. So hydrogen fusion essentially migrates from the core to a shell around the core. Meanwhile, the helium core will eventually get hot enough to ignite a new kind of fusion. It will start fusing helium into carbon. The star's internal structure rearranges: a small, dense, very hot core fusing helium and a shell around it fusing hydrogen. All this generates a tremendous amount of energy in the star's interior. The result is that the outer layers of the star are pushed outward, far outward. The star balloons in size. As the surface expands, it cools. The once yellow-white star becomes a cooler red star. It has now become a red giant. The term is literal. It is redder in color and gigantic in size compared to before. A star in this phase can swell to tens or even hundreds of times its original diameter. One day, about 5 or 6 billion years from now, our Sun will undergo this transformation into a red giant phase. As it approaches old age, it will exhaust the hydrogen in its core and begin fusing helium. The Sun's core will contract and heat up, and its outer layers will expand dramatically. In the process, the Sun's radius will likely grow so large that it engulfs Mercury and Venus, the two innermost planets, and comes perilously close to Earth's orbit. From Earth's perspective, the Sun would swell to an enormous red orb dominating the sky. the temperature on our planet would skyrocket. In fact, long before the sun's surface actually reaches Earth, the intense heat will boil away Earth's oceans and atmosphere and render our planet uninhabitable. Essentially, a scorched, lifeless rock. There is a chance Earth might be swallowed up entirely by the sun's expanded atmosphere, or it might just survive, parched and baked. Either way, the inner solar system will be unrecognizable. The sun will not only grow in size, it will also lose a lot of its mass via a powerful stellar wind. With less mass, the sun's gravitational pull on the remaining planets will weaken, causing those planets to drift outward to wider orbits. This red giant phase is a dramatic change, but fortunately for us, it's billions of years away in the future. For a star of the sun's mass, this red giant stage is essentially the beginning of the end. After perhaps a billion years in the red giant phase, the sun's core will have fused its helium into carbon and oxygen. It won't be hot enough to fuse those heavier elements, so the core will remain as a hot ball of carbon and oxygen. Without new fusion to support it, the core will contract further, and the outer layers of the sun, which expanded so far out, will become increasingly unstable. In a series of pulses, those outer layers will be expelled into space, creating a brilliant cloud of gas around the dying star. This glowing shell of ejected gas is called a planetary nebula. The sun, in its death throes, will thus cast off its atmosphere, which will drift away as an expanding bubble of gas. Planetary nebulae can be stunningly beautiful. Observed through telescopes, they appear as multicolored rings or shapes of glowing gas. In a few tens of thousands of years, the sun's shed gases will mix into the interstellar medium, enriching it with elements the sun made. All that remains of the sun at this point will be its former core. This exposed core is a hot, extremely dense orb about the size of Earth. It's called a white dwarf, the final state of a low to mid-mass star like our sun. A white dwarf no longer has fusion happening in its center. It is supported against further collapse by quantum pressure. It is, essentially, a stellar ember, an extremely hot cinder left over from the star's life. When it first forms, a white dwarf is incredibly hot and glowing white, blue, but it's also very small, so its total light is relatively faint. Over billions of years, it will cool and fade. To appreciate just how dense a white dwarf is, it packs roughly the mass of the sun into a volume the size of Earth. Imagine compressing something as massive as a star into a ball only 8,000 miles across. The density of such an object is mind-boggling, on average about 1,000,000 times denser than water, meaning a single cubic centimeter of white dwarf material would weigh on the order of 1 ton. In other words, a teaspoon of white dwarf matter would weigh several tons here on Earth. The gravity on its surface would be hundreds of thousands of times stronger than Earth's. If you somehow stood on a white dwarf, you would feel yourself weighing so much that you'd be crushed instantly. Over a very, very long time, a white dwarf will radiate away its heat and cool down. Eventually, after many tens or hundreds of billions of years, it would become a black dwarf, essentially a cold, dark, stellar remnant. In the case of our sun, this is its ultimate fate, to spend eternity as a faint white, hot star gradually cooling into darkness. Indeed, most stars end their lives quietly as white dwarfs, simply cooling and fading away. Only the most massive stars end in the spectacular supernova route. Now consider a star much more massive than the sun, say a star born with 10 or 20 times the sun's mass, or even more. These stars go through their lives much more quickly and violently. They too will leave the main sequence once their core hydrogen is exhausted, but the sequence of events is even more extreme. Such a star becomes a red supergiant instead of a mere giant. One of the best known examples of a red supergiant is Betelgeuse, the bright reddish star in Orion's shoulder. Betelgeuse is about 15,020 times as massive as the sun and has expanded to a tremendous size, Observations estimate it is on the order of 700–800 times the Sun's radius. If Betelgeuse were placed at the center of our solar system, it would extend well past the orbit of Mars and possibly even approach Jupiter's orbit. It's so large that its volume would encompass tens of millions of suns. And Betelgeuse isn't even the largest star known. A few rare hypergiant stars, such as UY Scuti or Stephenson 218, are believed to have radii around 1,500 × 2,000 times that of the Sun. Truly monstrous stars. These colossal stars are extremely luminous and short-lived. Betelgeuse, for instance, is only on the order of 10 million years old, yet it is already in its dying phase. In fact, Betelgeuse is expected to explode as a supernova in the relatively near future. It could happen anytime in the next 100,000 years, which is a blink of an eye for a star. It might be tomorrow, or it might be far beyond our lifetimes. We can't pinpoint exactly when, but we know the star is nearing the end of its life. When Betelgeuse does explode, it will likely shine as bright as the full moon in our sky for a few weeks and be easily visible even in daytime. What leads a star like Betelgeuse, or any other massive star, to such a violent end? The difference lies in what happens in the star's core after the hydrogen is used up. A high-mass star has the gravity and pressure to push the boundaries of fusion much further than a star like the Sun can. When hydrogen in the core runs out and the core contracts, the temperature soars high enough to ignite the fusion of helium into carbon and oxygen. Once helium in the core is exhausted, the core contracts and heats again, and the star's envelope expands into a red supergiant. But in these behemoths, the core gets hot enough to start fusing carbon into heavier elements. The pattern continues in a kind of fusion cascade. Carbon fuses into neon, magnesium, and sodium. When carbon is depleted, the core contracts and heats, and then neon fuses into oxygen and magnesium. Then oxygen fuses into silicon and sulfur. And finally, silicon fuses into iron and nickel. The star builds up onion like layers of fusion shells. Hydrogen burning in an outer shell, helium burning in a shell beneath that, carbon burning in a shell closer in, and so forth, all the way to a growing iron core in the center. The iron core is the final product of fusion, because fusion of iron doesn't release energy, it consumes energy. That's a crucial point. Up until iron, fusion can power the star. But once the core accumulates iron, further fusion would not yield net energy. So, as iron builds up in the core of a massive star, the star is living on borrowed time. The star continues burning elements in shells around the core, piling more and more iron into the center. Meanwhile, the time spent on each successive fuel is shorter and shorter. A massive star might spend millions of years fusing hydrogen, maybe 1 million years fusing helium, but perhaps only a few years fusing carbon, a few months fusing oxygen, and mere days fusing silicon into iron. Eventually, the iron core reaches a critical mass. At that moment, the star can no longer support its own weight. For a massive star, this is the final act, and it's dramatic. When the iron core can no longer hold itself up, it collapses catastrophically under gravity. This collapse happens incredibly fast. In under a second, the core implodes. The temperatures in the core skyrocket, and atomic nuclei get crushed together. Protons and electrons merge into neutrons, so the core essentially becomes one giant atomic nucleus, a ball of neutrons. The collapse is suddenly halted by the degeneracy pressure of neutrons. In that instant, the infalling material rebounds off the stiff neutron core. A powerful shockwave is sent roaring outward through the star's interior. The core collapse and rebound is so intense that it unleashes an enormous burst of neutrinos and a tsunami of energy. The star's outer layers are blown off in one of the most violent events in the universe, a supernova explosion. If the core of the star at the time of collapse is below about 2003 solar masses, it will become a neutron star, the ultra-dense city-sized stellar remnant composed almost entirely of neutrons. If the core is above that mass threshold, even the neutrons cannot halt the collapse, and the core will continue collapsing into a black hole, a point of practically infinite density. Either way, the core's collapse triggers the supernova blast. In a supernova, the star's entire outer structure is ripped apart. The star's brightness increases tremendously for a short time. A supernova can briefly outshine an entire galaxy of normal stars. Imagine a single star suddenly shining brighter than 100 billion stars combined. That is what a supernova can do. It will radiate as much energy in a few weeks as the Sun will in its entire 10 billion year lifetime. If such an event happens relatively nearby, it can be visible from Earth, even in the daytime. Human astronomers have indeed witnessed supernovas in the past. Historical records from East Asia and the Middle East describe guest stars appearing in the sky. For example, in 1054 AD, Chinese astronomers noted a new star that was visible in daylight for weeks. This was a supernova. Another supernova was observed in 1604. More recently, in 1987, a star exploded in the Large Magellanic Cloud and could be seen by the naked eye. In our own Milky Way, no supernova has been observed in the past 4 centuries, but statistically, we expect a few per century meaning we could be due for another any time in the future. In the chaotic violence of a supernova, there is a remarkable silver lining. This is the event that forges many of the heavy elements that enrich the universe. During the star's normal life, it created elements like carbon, oxygen, and silicon in its core. But elements heavier than iron, such as gold, platinum, and uranium, require the extreme conditions of a supernova to form. In the supernova blast, atomic nuclei slam together in rapid fire reactions, building up many of the heaviest elements on the periodic table. The explosion then scatters these newly forged elements out into space. The stellar ashes, carbon, oxygen, calcium, iron, gold, and so on, are flung far and wide, mixing into the gas between stars. Supernovae are therefore cosmic gardeners, seeding the interstellar medium with the ingredients for future generations of stars and planets. The very material that makes up our Earth and our bodies has gone through this cycle. The iron in your blood, the calcium in your bones, the oxygen that you breathe, those atoms were once created in the interior of a star or in a supernova explosion. As a NASA astrophysics team put it, we truly are made of stardust. The calcium in your teeth, the iron in your hemoglobin, the carbon in your DNA, all were forged in stellar furnaces. Indeed, without the carbon, oxygen, nitrogen, and other elements spread by stars, Earth could not have solid ground, air, or water, and life as we know it would be impossible. We owe our existence to stars that died long before the Earth formed. Indeed, without the heavy elements from stars, there would be no rocky planets, no air or oceans, and no living beings. Meanwhile, what's left of the star's core becomes either a neutron star or a black hole, as mentioned. Neutron stars are fantastical objects. Imagine something more massive than our Sun crushed into a sphere only about 20 kilometers across. They are so dense that a single teaspoon of neutron star material would weigh around 1 billion tons on Earth. The gravity on its surface is so strong that if you dropped an object from 1 meter above, it would hit the surface in a microsecond, accelerating to millions of kilometers per hour. Neutron stars often spin rapidly. Some rotate multiple times per second and emit beams of electromagnetic radiation from their magnetic poles. As they spin, these beams sweep around like lighthouse beams. If such a beam points toward Earth periodically, we see pulses of radiation. These are observed as pulsars. The first pulsar was discovered in 1967 as a mysterious radio pulse every 1.3 seconds, so regular that the discoverers jokingly nicknamed it LGM-1. half, seriously wondering if it was a signal from an alien civilization. We now know it was a rapidly spinning neutron star. Pulsars can spin unbelievably fast. The fastest known pulsar rotates more than 700 times per second. Imagine an object more massive than the Sun, spinning hundreds of times a second. It defies the imagination. Some neutron stars, called magnetars, have magnetic fields even more extreme, up to 1,000 times stronger than a typical pulsar. A magnetar's field is so extraordinarily powerful that, at a few thousand kilometers away, it could disrupt electronics on Earth. Occasionally, magnetars undergo starquakes that release giant flares of X-rays and gamma rays. If the star's remnant core was too massive to form a stable neutron star, it continues collapsing beyond even the neutron stage. In that case, the core becomes a black hole, an object with gravity so intense that nothing, not even light, can escape from its vicinity. A black hole formed from a single star might contain, say, 5 or 10 solar masses of material, but all of that mass is crushed down into an infinitesimally small volume at the center. The region around it from which not even light can escape is called the event horizon, effectively the point of no return. For a black hole with the mass of our Sun, the event horizon would be only about 3 kilometers in radius. If the Sun was somehow compressed into a sphere only 6 kilometers across, it would become a black hole. For something as massive as Earth, the event horizon would be barely a centimeter across, meaning Earth would have to be crushed to the size of a marble to turn into a black hole. These numbers illustrate how incredibly dense and compact black holes are, matter and gravity in their most extreme state. Because no light comes from a black hole itself, we cannot see a black hole directly as a glowing object. A lone black hole floating in space would appear truly black, a gravitational trapdoor in the cosmos. However, we can detect black holes by their effects on surrounding matter. Often, a black hole will have gas around it. That gas forms a swirling accretion disk as it spirals into the black hole, and it gets extremely hot, often emitting X-rays that telescopes can detect. We also observe stars orbiting an invisible mass. For example, the center of our Milky Way galaxy has stars whipping around an unseen object, which we know is a supermassive black hole. In recent years, astronomers have even managed to capture direct evidence of black holes by imaging their silhouettes. In 2019, the Event Horizon Telescope project released the first picture of a black hole, or rather, of the glowing gas around a black hole's event horizon. It showed a ring of light and a dark central shadow, exactly as predicted by physics. This was the supermassive black hole in a distant galaxy. And in 2022, we finally saw a similar image of the supermassive black hole at our own galaxy's center. Black holes, once purely theoretical, are now actively studied cosmic phenomena. Amazingly, even after a star has died, its story might not be completely over. Sometimes, the remnants left behind can have dramatic afterlives. For example, if two neutron stars eventually orbit each other, they will gradually spiral inward over time. After millions of years, they may collide in a spectacular event called a kilonova, a merger explosion even more energetic than a typical supernova. Such mergers produce strong bursts of gravitational waves that propagate outward. In 2017, scientists detected gravitational waves from a neutron star collision and also saw a flash of light from it. This was the first time we observed both gravitational waves and electromagnetic radiation from the same event. That neutron star merger forged copious amounts of heavy elements and scattered them into space. Black holes can merge with each other too. When they do, they emit a flood of gravitational waves. We can't see the merger, but detectors on Earth can hear the fabric of space tremble. In 2015, LIGO observed such signals for the first time, confirming a major prediction of Einstein's theories. These phenomena show that even in death, stars can continue to influence their surroundings in extraordinary ways. After a supernova fades, all that remains of the star may be a dense remnant, plus an expanding cloud of gas and dust, the supernova remnant. The ejected material from the star, now racing outward, sweeps up the surrounding interstellar gas and dust, creating a shell or complex filamentary structure that can glow for tens of thousands of years. The Crab Nebula, for instance, is the beautiful filamented remnant of the supernova of 1054 AD, still expanding at thousands of kilometers per second. Over time, these remnants disperse and mix with the interstellar medium. And here, the grand cycle turns anew. The scatterings of old stars eventually become part of new nebulae, providing the enriched raw material for future stars. The next generation of stars will form out of clouds, seeded with the heavy elements of previous generations. Our Sun is thought to be a late generation star, born roughly 4.6 billion years ago from a nebula already seeded with heavy elements by earlier supernovae. Those elements made it into our Earth and into us. We truly are, as the saying goes, children of the stars. Stars, then, are not only beacons of light, but cosmic alchemists and recyclers. Through their life cycles, they transform the primordial hydrogen and helium into a rich array of heavier elements. And through their deaths, they redistribute those elements across space to fertilize new star formation. Generations of stars have built up the carbon in our tissues, the oxygen in the air, the silicon in rocks, and every atom of every element heavier than helium. The universe began with mostly hydrogen and helium, and it is the stars that fashioned all the rest inside their hot cores. It's a magnificent ongoing circle of stellar evolution and renewal, star birth, star life, star death, and new stars born from the remnants. This cycle has been going on for billions of years and will continue for billions more. It is the engine that drives the chemical enrichment and dynamic evolution of galaxies. When we survey the night sky filled with stars, we are gazing at a vast cosmic ecosystem in action. Each pinpoint of light has its own history and future. Some of those stars may be like our Sun, gently burning for eons. Others might be giant stars soon to explode, or faint red dwarfs just chugging along. There are hundreds of billions of stars in the Milky Way galaxy alone, and beyond that, billions of other galaxies each with their own billions of stars. The total number of stars in the observable universe is estimated to be around 10 to the 22. That's a 1 with 22 zeros after it. This number is so huge that it defies true comprehension. One popular comparison is that there are more stars in the universe than grains of sand on all the beaches on Earth. In fact, astronomers estimate there are on the order of 10,000 stars for every grain of sand on Earth. It's an astonishing thought. Next time you're at the beach, pick up a handful of sand and consider that the stars outnumber those tiny grains. Every one of those stars is a sun, and many of those suns have their own families of planets. The universe is teeming with stars beyond counting. Understanding the life cycle of stars gives us a profoundly richer appreciation of the night sky. When you next gaze up at the stars, remember that those twinkling lights are not mere points. They are distant suns, each with a life story spanning eons. The star that looks like a pinprick could be a giant blazing at millions of degrees, or a diminutive red ember glowing softly. Some of the stars you see tonight might already have exploded in the far past, their light only now arriving at Earth after traveling for centuries through space. In a very literal sense, we are connected to these stars. Our planet and our bodies are composed of star-born atoms. Indeed, without the heavy elements forged in stars, Earth wouldn't exist as a rocky world, and human beings could not have come to be. As the late astronomer Carl Sagan famously said, "We are made of star stuff." We are the universe's way of knowing itself, formed from the ashes of long dead stars. In the end, the saga of stars is the saga of the universe. It's a story of creation and transformation on an epic scale, of diffuse gas gathering to ignite nuclear fire, of shining stability and convulsive death, of elements forged in celestial furnaces and cast into the darkness to become the seeds of new worlds. Stars have illuminated the cosmos for over 13 billion years, and they will continue to do so long into the future. Every twinkling star in the sky is a testament to the ongoing cycle of cosmic birth and rebirth. So the next time you find yourself under a starry night, take a moment to ponder the incredible processes happening above you. Those stars are distant suns, forging the stuff of life, exploding and renewing the galaxy. They light up the darkness and spark our imaginations. Theirs is a never-ending story, one of fire and dust, life and death, and renewal. An endless cosmic dance that has shaped our universe and, ultimately, made our own existence possible. And as long as you can see the stars shining overhead, you are witnessing a part of that grand story unfolding, a story that connects us all to the cosmos and to the dazzling stars that fill the sky. The final glow of the previous story fades, but our journey among the stars is far from over. In fact, it's only just beginning. Out in the cosmic dark, countless stars still beckon with new mysteries and deeper roles to explore. We have gazed upon the life cycles of stars, their births in nebulous cradles and their deaths in explosive finales. Yet there is even more to the stellar saga. Now, let us venture further into the galactic tapestry to uncover how stars themselves shape the grand story of the universe. As we continue, imagine drifting back in time to an era before even the first star ignited. In that primordial darkness, over 13 billion years ago, the universe waited for its first light. When the first generation of stars were finally born, they were unlike any that exist today. These population 3 stars, as astronomers call them, were forged from only the simplest elements, the sole ingredients created by the Big Bang. Theory paints them as cosmic titans, perhaps 30 to 300 times the mass of our Sun, and millions of times brighter. Such massive stars would burn their fuel ferociously fast, blazing only a few million years before dying in titanic supernova explosions. Yet in their brief lives, they performed a vital service. Their searing ultraviolet light rayonized the universe's hydrogen, ending the cosmic dark ages nearly 1 billion years after the Big Bang. In those first brilliant sparks, the universe transitioned from dark and opaque to radiant and transparent, a fundamental turning point in cosmic history. When those primordial stars lived and died, they also created something entirely new: heavy elements. In their hot cores, nuclear fusion began forging elements heavier than helium, carbon, oxygen, silicon, and more. And when the first stars perished as supernovae, they seeded the cosmos with these heavier elements. Before stars, the universe lacked the ingredients for planets or life. After the first stars, space was enriched with the star stuff from which future generations could build. It's awe-inspiring to realize that nearly all the elements in our bodies, the calcium in our bones, the iron in our blood, the oxygen we breathe, were forged in the hearts of stars that lived long ago. Those early explosions scattered the raw materials for new stars, new planets, and eventually us. Little wonder that astronomer Carl Sagan's poetic truth resonates. We are made of star stuff. The universe had to go through the fires of stellar furnaces to fill the periodic table beyond hydrogen and helium. With each generation of stars enriching the cosmic brew, subsequent stars were born with higher metallicity. Thus began an ongoing chemical evolution, each stellar generation shaping the composition of the next, gradually building up the complexity needed for rocky worlds and living beings. In the wake of the first stars, new generations of stars began to form from the ashes. Astronomers classify these stellar populations by their metal content. The ancient stars that followed the primordial ones are dubbed Population 2. They contain only a small trace of heavy elements, just a smattering inherited from those first supernovae. Many Population 2 stars still shine today. They are the oldest stars in galaxies, often found in the halos of galaxies or in ancient globular clusters. In fact, some globular star clusters in our Milky Way are nearly 13 billion years old, almost as old as the universe itself, and their stars preserve a fossil record of the early cosmos. These venerable suns are cosmic time capsules, their faint metal content telling us they formed when the universe was still poor in heavy elements. By contrast, Population Y stars, like our own Sun, are rich in heavier elements. Population I stars are younger, born later in cosmic history, from gas already recycled and enriched by countless prior stellar lives. They reside mostly in galactic disks and include many bright, hot stars, as well as middle-aged stars like the Sun. The distinction between these populations isn't just academic. It's central to understanding how galaxies formed and evolved. In the Milky Way, for example, the spherical halo of old Population 2 stars may be remnants of the galaxy's original build and early mergers, whereas the disk's Population 1 stars reflect ongoing star formation fueled by interstellar gas. The very structure of our galaxy, a thin disk with spiral arms, a central bulge, and a diffuse halo, has been shaped by the continuous birth and death of stars over billions of years. Early in our galaxy's youth, it likely underwent titanic mergers with smaller protogalaxies. One dramatic merger, revealed by the European Gaia spacecraft's star mapping data, occurred around 10 billion years ago when the Milky Way swallowed a dwarf galaxy, now nicknamed Gaia Enceladus, or the Gaia Sausage. This cosmic collision delivered a vast influx of stars into the Milky Way's halo. The evidence is written in the motions and chemical makeup of many halo stars, which are distinct from native Milky Way stars, a sign that they originated in another galaxy. During such mergers, bursts of star formation likely ignited as gas clouds were jolted and compressed. Thus, the Milky Way's early history, the thickening of its disk, the build up of its stellar halo, was driven in part by starbirth sparked in the chaos of mergers. Time and again, galaxies grew by merging and forming new stars, with each generation of stars influencing the galaxy's structure and dynamics. Star formation itself tends to be a self-limiting and self-propagating process. Massive young stars radiate intense light and spew stellar winds, which can carve cavities in the surrounding gas. When the most massive of these stars go supernova, they blast the gas with shockwaves. This feedback can either trigger new stars or quench star formation. In dwarf galaxies, a few vigorous supernovae can blow out much of the gas, stifling further starbirth. In larger galaxies, star formation and supernova feedback regulate each other in a complex dance, ensuring that galaxies don't convert all their gas into stars at once. Indeed, observations show that the universe's star formation rate peaked about 10 to 11 billion years ago and has been declining ever since. At its height, galaxies were forming stars at a frenetic pace, so much so that today's rate is only a few % of that peak. Over billions of years, much of the free gas in galaxies has been used up or locked into stars, and energetic feedback from stars has kept a lot of remaining gas too hot to collapse easily. Our cosmos is slowly simmering down. Still, new stars continue to be born even now, especially in the rich spiral arms of galaxies. In our Milky Way, stellar nurseries like the Orion Nebula are actively turning out fresh stars. But the overall trend is inexorable. The fuel for star formation is finite, and eventually it will run low. Gazing far into the future, astronomers estimate that in roughly 100 trillion years, all the usable star-forming gas will be exhausted or locked up. By that far epoch, the era of star formation will draw to a close. The universe will transition into a quieter stage, dominated by the embers of stellar evolution, myriad white dwarfs slowly cooling into black dwarfs, neutron stars and black holes lurking in the darkness, and only the occasional new star flickering to life from the rare merger of two old stellar remnants. But fear not. At present, the universe is still richly populated with shining stars, and we live in a cosmos that is very much alive with stellar light. Let's turn our attention to the stars as architects of their galaxies. Every galaxy's visible beauty, its shimmering starlight, its glowing nebulae, comes from stars. Stars delineate the spiral arms of disk galaxies, with luminous young star clusters tracing out spiral patterns like celestial fairground lights. In majestic barred spirals and elegant ellipticals alike, the collective light of billions of stars gives each galaxy its form and color. Hot, young stars glow blue, white, giving star, forming galaxies a bluish hue, while older, cooler populations lend a yellow-red warmth to galaxy bulges and ellipticals. Thus, the mix of stellar ages influences a galaxy's appearance. A young, actively star-forming galaxy looks very different from an old, evolved system, precisely because of its stars. Over cosmic time, galaxies can even change type as their star formation slows. A disk galaxy may fade and redden into something more akin to an elliptical if star birth ceases and its blue stars die out. The grand narrative of galaxy evolution is intimately tied to the cycles of star formation within. Now consider not just individual stars, but stars in pairs and groups. It may surprise you to learn that most stars in the sky are not solitary like our Sun, but part of binary or multiple star systems. Imagine two stars locked in a gravitational waltz, orbiting a common center of mass. Such binary star systems are incredibly common, by some estimates, more than half of all Sun. Like stars have a stellar companion. In these systems, stars can profoundly affect each other's evolution. Sometimes one star will swell into a red giant and transfer mass to its companion, an event that can spark explosive outbursts or novae. In fact, one type of supernova occurs in an elderly binary. A dense white dwarf star siphons gas from a companion until a runaway explosion is triggered, obliterating the white dwarf. These Type Ia supernovae are immensely important standard candles that have helped astronomers measure cosmic distances and the expansion of the universe. The discovery of the accelerating expansion of the universe, and hence dark energy, hinged on observations of distant Type Ia supernovae. Thus, an intimately interacting binary pair on the stellar scale produces a beacon visible across billions of light years, allowing us to gauge the universe's fate. In other binaries, two massive stars might evolve in tandem and eventually merge or collide. In globular clusters, such stellar collisions can produce the enigmatic blue straggler stars, stars that appear unexpectedly young and blue in a cluster of otherwise old stars. Blue stragglers are thought to form when two stars coalesce into a single, more massive star, effectively rejuvenating it. The result is a star that stands out as bluer and more luminous than it should for the cluster's age, a literal stellar oddball that reveals the cluster's dynamic past. The overcrowded cores of globular clusters facilitate such collisions, offering yet another example of how stellar interactions can yield peculiar outcomes. Some binaries consist of extremely exotic partners, for example, a neutron star or black hole orbiting a normal star. These systems can produce astonishing phenomena like X-ray binaries and even the recently detected gravitational waves. Picture a dense neutron star, essentially a city-sized atomic nucleus with the mass of the Sun, pulling gas off a companion star. As the gas spirals in, it heats up and emits powerful X-rays, making the binary shine brightly in X-ray light. In 1967, astronomers discovered pulsars. The first was affectionately nicknamed LGM-1 for Little Green Men 1, because its precise radio pulses were so mysterious, they were jokingly suspected to be alien signals. Soon, pulsars were understood as rotating neutron stars, the collapsed remnants of supernova explosions. In some binaries, two neutron stars orbit each other, gradually spiraling as they radiate gravitational waves. In 2017, humanity observed for the first time the space-time ripples from such a neutron star merger, along with a dazzling multi-wavelength light show called a kilonova. That single event confirmed that neutron star collisions forge many of the universe's heaviest elements, and demonstrated how closely stellar death and cosmic alchemy are intertwined. Similarly, the first direct detection of gravitational waves in 2015 came from a merger of two stellar mass black holes, remnants of massive stars that had danced together until coalescing. These gravitational wave discoveries opened a whole new window on the universe, essentially hearing the sound of stars merging in the dark. Through binaries and their sometimes violent interactions, stars have enabled us to confirm Einstein's theories, understand extreme states of matter, and even create new fields of astronomy. While many stars live in pairs or clusters, our sun stands alone. Yet the sun is no less influential for its solitude. It anchors our solar system, and its steady light allowed life to flourish on at least one world. The sun's story is still unfolding. About 5 billion years from now, it will swell into a red giant, becoming so large that it engulfs Mercury and Venus, and possibly Earth as well. By then, Earth will be a scorched cinder. As the sun expands, it will also begin to blow off its outer layers. In its death throes, it may create a beautiful planetary nebula, a glowing shell of expelled gas, before finally settling down as a white dwarf. This stellar remnant, about the size of Earth but containing nearly half the sun's mass, will slowly cool like a fading ember for trillions of years. That is the long-range fate of our sun and stars like it, to quietly shed their outer envelopes and leave behind dense cores. The galaxy will become littered with these white dwarfs, cosmic embers that, though faint, carry the memory of their progenitor stars. Even in death, stars continue to shape their surroundings. When a massive star explodes as a supernova, it leaves behind either a neutron star or a black hole. The expanding supernova remnant, a glowing cloud of ejected material E, can crash into surrounding clouds and trigger new rounds of star formation. Think of the Crab Nebula, the remnant of a supernova observed in 1054 AD. At its center lies a whirling pulsar energizing the nebula, and around it, the expanding filaments are rich in elements like oxygen, nitrogen, and iron, synthesized in the star's final moments. Those elements will eventually mix into interstellar space, seeding future molecular clouds. In this way, each supernova is both an ending and a beginning. An ending for a massive star, but a beginning for new stars that will one day condense from the enriched debris. Meanwhile, the neutron star left behind pours out winds of high-energy particles, sculpting and illuminating the nebula. A stellar corpse can thus continue to inject energy into the galaxy's ecosystem long after the star's death. Black holes, too, play a role. If a stellar mass black hole devours gas or stars, it converts that mass to energy, impacting the ambient gas. And on a galactic scale, supermassive black holes lurking in galaxy centers, themselves the end, products of stellar processes and mergers can profoundly influence star formation in their host galaxies by blasting out energy. But those supermassive black holes are a tale for another time. In our story, we focus on the stars themselves, the little black holes they leave behind, and how even those contribute to the cosmic tapestry. Consider for a moment the sheer number of stars out there. Our Milky Way alone holds on the order of 100 to 400 billion stars. It's a figure almost beyond comprehension, and yet the Milky Way is just one of perhaps hundreds of billions of galaxies in the observable universe. If each of those has 100 billion or so stars, you get numbers like 10 more 22 stars in the observable universe. That's a 1 with 22 zeros after it, a quantity of stars truly staggering to contemplate. Each of those stars is a potential sun, perhaps with its own family of planets. In recent decades, we've learned that planets abound around other stars. The once singular idea of another solar system has given way to the realization that planetary systems are commonplace. Using missions like Kepler and TESS, astronomers have detected over 5,000 confirmed exoplanets so far, and counting. Statistics indicate that perhaps 1 in every 5 sun-like stars harbors an Earth-sized planet in its habitable zone. This means when you gaze up at the night sky, statistically the nearest sun-like star with an Earth-ish planet might be only a dozen light years away, practically next door on the cosmic scale. Planetary systems come in a dizzying variety: hot Jupiters, skimming their stars' surfaces, multi-planet systems packed in tight orbits, planets around double stars, and even planets orbiting the crushed remnants of dead stars. There are even planets wandering alone in the dark of interstellar space. Stars and planets are inseparable companions in the cosmic story, and just as stars give birth to planets, planets can influence stars in subtle ways.
Take our solar system. The sun's activity and stability have been key to life's development on Earth. Our sun is a rather steady star, but not all stars are so calm. Many young stars and red dwarfs are highly variable and prone to flares. Variable stars in general constitute a broad category, including stars that intrinsically pulsate, erupt, or have eclipsing companions, causing dips in light. These variations have made certain stars vital tools for measuring cosmic distances. For instance, the Cepheid variables, luminous pulsating supergiants, have a well-defined relationship between their pulsation period and true brightness. Discovered by Henrietta Leavitt over a century ago, this relationship allows astronomers to determine a Cepheid's distance by comparing its known true brightness to its observed brightness. Using Cepheids as standard candles, Edwin Hubble measured the distance to the Andromeda galaxy in the 1920s, discovering that Andromeda lay far outside our Milky Way, thus proving that the universe is populated with myriad galaxies. Later, Cepheids and Type Ia supernovae would help establish that the universe is expanding and, in fact, accelerating in its expansion due to mysterious dark energy. It's poetic that the rhythmic beating of variable stars' light has served as a cosmic yardstick, allowing us to map the universe at large. A throbbing Cepheid in a distant galaxy becomes a beacon, indicating that galaxies' distance, and hence offering insight into the scale of the cosmos. Not all variable stars are so regular and helpful. Some are downright capricious. There are flare stars that can double in brightness in minutes, eruptive variables like young stellar objects that burp out bursts of light as they gulp down fresh gas from their surroundings, and giants like Mira, a star in Cetus that pulsates over many months, varying so much that it can nearly disappear from view and then return. And who could forget the recent drama of Betelgeuse, the red supergiant shoulder of Orion? In late 2019, Betelgeuse dimmed startlingly, losing 2/3 of its brightness, causing speculation that it might be about to explode as a supernova. Observations eventually indicated that Betelgeuse had likely ejected a cloud of dust that temporarily obscured its light from our vantage point. By mid-2020, Betelgeuse returned to normal. This episode was a vivid reminder that stars are dynamic, evolving entities, not static points of light. Betelgeuse is expected to go supernova sometime in the next 100,000 years, a blink of an eye in cosmic terms, and when it does, it will light up our sky brilliantly for weeks, a spectacular final act for a star perhaps 15,020 times the sun's mass. If we're lucky enough to witness it, That supernova will be a momentous event in human skywatching history. But even short of such cataclysms, the variability of stars teaches us about their inner workings. Through the field of astroseismology, astronomers study tiny pulsations in stars to infer their internal structures, analogous to how geologists use earthquakes to probe Earth's interior. Our Sun, too, has a mild 11th-year cycle of activity, modulating its sunspots and flares, which subtly affects solar output. Thankfully, the Sun's variability is slight. A more erratic star might have made Earth's climate far less stable for life. Stars, then, are creators, testers, and timekeepers of the universe. They create the elements that form planets and people. They test the laws of physics in extreme conditions, from nuclear fusion in cores to relativistic speeds in neutron stars. They serve as timekeepers by revealing cosmic distances and ages through their life stages and variable rhythms. And collectively, stars brighten the universe, turning the primordial darkness into a cosmos of light and color. It is sobering and fascinating to realize that the universe's era of starlight is, in a sense, a finite chapter. We live roughly in the middle of this chapter. For billions of years before stars, the universe was dark, and trillions upon trillions of years in the future, after the last stars have flickered out, the universe will go dark again. But right now, and for many eons to come, it is the age of stars. An age in which galaxies sparkle and life has the opportunity to arise on warm, sunlit worlds. The story of stars is also the story of continuity and renewal. Massive stars live fast and die young, but in doing so, they trigger new growth around them. We see this in regions like the Carina Nebula, where the death of one generation seeds nebulae that birth the next. In a spiral galaxy's life, waves of star formation move through the disk, often stimulated by spiral density waves or past encounters with other galaxies. Our own Sun likely formed in a cluster with dozens or hundreds of other stars about 4.6 billion years ago, possibly triggered by a nearby supernova explosion that compressed our natal cloud. Traces of that supernova may be preserved in certain isotopes found in meteorites from the early solar system. Thus, the Sun and planets might owe their existence to the death of a long-gone massive star. Indeed, each of us carries the ashes of ancient supernova inside our bodies. The iron in your blood was forged in a star that exploded billions of years before the Sun even existed. In a very literal sense, stars are our cosmic ancestors. As we look ahead, what new revelations about stars await us? We stand in an exciting era of astronomy. The James Webb Space Telescope is now peering into the deep cosmos, possibly capturing light from some of the first galaxies and stars that formed over 13 billion years ago. Already, Webb has identified candidate galaxies so far away that they challenge our understanding of how quickly stars and galaxies could have formed. In the coming years, Webb may indirectly detect evidence of population 3 stars, or at least constrain their properties by observing the distant galaxies they inhabit. On the other end of the spectrum, Webb and other observatories are turning their gaze to exoplanet atmospheres, reading the fingerprints of molecules like water vapor, carbon dioxide, and methane as starlight filters through alien skies. In 2022, JWST made the first clear detection of carbon dioxide in an exoplanet's atmosphere, a proof of concept for the detailed atmospheric analysis of potentially habitable worlds in the future. We are learning to read the chemical weather reports on planets dozens of light years away, an astounding development. Future missions will go even further. The upcoming Nancy Grace Roman Space Telescope will conduct vast surveys of the Milky Way's center, potentially discovering thousands of new exoplanets through microlensing and mapping out the distribution of stars and dark matter with high precision.
The European Extremely Large Telescope, a 39-meter behemoth currently under construction, will in the next decade directly image some exoplanets and dissect the light of stars in distant galaxies, perhaps even detecting biosignature gases on rocky planets around nearby stars. It is mind-boggling. We are on the cusp of potentially finding evidence of life beyond Earth by examining starlight passing through a distant planet's atmosphere. Should we succeed, it would be a profound confirmation that we are not alone, all made possible by the interplay of stars and their planets. Even without finding life, the future of stellar astronomy is bright. New observatories will allow us to watch stars in real time in unprecedented ways, catching the precise moment a star goes supernova in our galaxy, or detecting the subtle vibrations of stars across our galaxy to decode their ages and compositions. We might witness phenomena we've only theorized, perhaps the birth of a black hole accompanied by a flash of neutrinos and gravitational waves, or the mergence of two white dwarfs into a new star or a supernova. We may even discover new classes of stars. Who knows? Throughout history, whenever we have opened new eyes on the universe, we've stumbled upon surprises. There could be rare types of stellar objects out there awaiting discovery, stars powered by exotic physics, or stars caught in transitions never before seen. The universe tends to be creative with its use of the physical laws. From the first luminous beacons that banished the cosmic night, to the ordinary middle-aged sun that sustains life on a blue planet, to the spectacular supernovae and gravitational wave chirps that herald stellar deaths, stars have been the main protagonists in the cosmic drama. They are the alchemists that forged the elements, the lighthouses that guide our explorations, and the engines driving the evolution of galaxies. As we float here on our tiny world, bathing in the gentle sunshine of our star, we remain intimately connected to the lives of stars across the universe. Every atom of calcium in your bones was fused in a star that lived long ago and far away. Every gentle sunset tinged with reds and oranges is a reminder that our sun, too, will one day swell and cast a red hue over the sky of whatever beings inhabit Earth in the distant future. Yet even as individual stars perish, the universe ensures the torch of light is passed on. New stars ignite from the ashes, continuing the cycle. And so, the cosmic roles of stars are as profound as they are varied. Stars are creators of light, of elements, of new beginnings. Stars are destroyers. In their violent ends, they can obliterate companions or outshine entire galaxies for a time. Stars are storytellers. Their compositions and motions recount the history of their galaxies. Stars are guideposts. Their steady pulsations and explosions have built our cosmic distance ladder and expanded our knowledge of the universe's expansion. Stars are nurturers, providing warmth and energy to any orbiting planets, and perhaps nurturing life. It is often said that without stars, the universe would have remained a dull, cold fog of hydrogen and helium. There would be no planets, no complex chemistry, and certainly no people to wonder at it all. Indeed, without the stars, the universe would lack its narrative spark. Our exploration of the stars deepens our connection to the cosmos. When we look up on a clear night and see the Milky Way's band of light, we are seeing the integrated glow of billions of distant suns, many of them older, many younger, each on its unique journey from birth to death. Among them are red giants, white dwarfs, neutron stars, perhaps even black holes quietly lurking. All of them together create the shimmering tapestry of the night sky. As we conclude this chapter of the documentary, let's reflect on the awe that stars inspire. For thousands of years, humans have looked to the stars for constancy, for navigation, for myths and meaning. Only in the last century or so have we truly grasped what they are. Nuclear furnaces, balanced by gravity, simple in their basic principles, yet endlessly diverse in their outcomes.
And only in the last few decades have we come to see the universe on the largest scales and realize the full extent of the stars' role in shaping everything. The saga of stars is ongoing. Even now, new stars are being born in dusty nebulae. Old stars are blowing themselves apart. Binary stars are merging. Planets are coalescing around nascent suns. Life might be evolving in some distant solar system under the light of an alien star. And photons that left stars billions of years ago are just now reaching Earth, bringing us news from across the universe. With each advance in technology, we become better listeners and observers of the stars' messages. In the near future, we might map the surfaces of stars' light years away, or detect the faint whispers of stars collapsing into black holes across the universe. And someday, perhaps, we will travel to other stars, our descendants, voyaging across interstellar space to touch those points of light that have beckoned for ages. For now, we continue to study and marvel. The stars have been our beacons, our ancestors, our catalysts. They will continue to shine for billions of years, but not forever. So it is a privilege to exist in this epoch of glittering skies. As our story winds down, step outside on a dark night and look up. Each star you see is part of a grand cosmic ecosystem. Some of those stars are likely orbited by planets you cannot see, perhaps harboring beings who look back at our sun as just another point of light in their sky. In the end, stars connect us across the gulfs of space and time. They are the universals, appearing in the sky of any planet in any galaxy, adhering to the same physics, telling variations of the same tale. This is the cosmic role of the stars, to light up the universe, to forge atoms from the raw stuff of the Big Bang, to sculpt galaxies, to cradle planets, and to continuously renew the cosmos. They are the glittering thread woven through the fabric of space, time, binding the universe together in light. And as long as stars shine, the universe will not be a lonely, lifeless place, for their light creates the possibility for beauty, complexity, and life. The story of stars is the story of how the universe, once a primordial soup of particles, became self-aware through creatures like us. We are the children of the stars, and through us, the stars know themselves. In the ever-continuing cycle of cosmic evolution, the stars have truly shaped the evolution of the universe, and they will continue to do so far into the future. So, whenever you stargaze, remember, you are watching creation in action, witnessing the ongoing drama that made all of existence possible. The tale of the stars is the tale of us all, a story still unfolding, written across the sky in the light of a billion suns.